Well, welcome everyone to the third day of our conference, Near Zero Carbon Combustion Technology, which is run here from the Center, Clean Combustion Research Center at King Abdullah University of Science and Technology, KAUST. We had really 2 successful days, and we're looking to have an interesting today insights into where we're going in terms of decarbonization, especially in the heavy industry. We have 8 world-leading speakers and in topics that are of great interest to many of you here in the audience and also online. This afternoon is made of 2 sessions. The first one is looking at general sort of insights into the industry and how do we decarbonize it. So we're covering most of the heavy industry, from steel to aluminium to cement, but also we're starting with more sort of a broader perspective about the field and also about what's happening here in the kingdom. And then the second session will be more on renewable technology and how can they be applied into this what's called hard to abate sort of type sectors. The format is that we're going to have a keynote speaker for 30 minutes, followed by 4 invited talks, each for 15, and then we're going to have a panel discussion. I'm going to encourage you all to write your questions and answers as they come to your mind. Don't wait to the end. And then some of them will be answered online, and some of them will be able to read. So all of us would be sort of hear him and discuss him. Please participate and to maximize the benefits out of this session. It gives me great pleasure to introduce our first speaker, Cedric Philibert. He's a senior analyst of energy and climate with a focus on renewable energy and industry and transport, electrification, and hydrogen. It's quite a broad portfolio in the IFRI in France. Obviously, most of you may have heard of Cedric originally in the IEA, where he worked for 20 years as a climate change policy on climate change policies and renewable energy technologies. He authored a very important book about, a report on decarbonizing the industry in particular. You may not know that he's a journalist by training, which is a handy thing to know if you want to be a communicator, and he definitely is a very good communicator. Obviously, he published a lot of papers and have contributed advisory to the Environment Minister and others. Today's topic that Cedric has chosen to give is international trends in decarbonizing heavy industry, roles of electricity, hydrogen, and synthetic fuels. And we look forward to Cedric's talk. Please, the floor is yours.
Well, thank you very much, Bassam, and please let me thank the organizers for inviting me to this important conference. I'm particularly pleased to be in that session with very good colleagues, and I will listen to them, and I'm sure we'll have a very interesting panel discussion after all these talks. Let me now try to share my screen and get into the presentation. Here we are. I hope it works. Can you see it? Okay.
Yes.
Very good. So you already said what was my presentation about: roles of electricity, hydrogen, and synthetic fuels in international trend in decarbonizing heavy industry. Oops. Yes. And I will start obviously with this very important report the IEA has published about a month ago, possibly the most important report in the life of the IEA, how to go to net zero by 2050 for the global energy sector. It has been very widely communicated, many press articles on this really important report. it marks a change in the policy of the IEA, and we'll see that immediately with this vision of how we're going to produce electricity by 2050 globally. And you see here the two major contributors to electricity generation that will be wind power and solar PV. They are the two here that go up to the sky in thousands of terawatt hours. And you see here the shares. So it will be solar and wind. And then if you add some other renewables, the total will be close to 90%. There will be very little unabated gas or coal. You will have some fossil fuels with CCUS, carbon capture and use or storage, and some nuclear. Nuclear is increasing. It's not nuclear that is replaced by renewables. It's the fossil fuels that will be replaced by renewables on a massive scale, which requires a big acceleration of the deployment of solar and wind electricity generating capacities. Still, biomass matters in this world and is a third pillar of a low carbon energy world. If you look now not at electricity, but at total energy supply, you see that you have, again, a lot of renewables, but the ubiquity and versatility of bioenergy mean that it will be used directly in many places, and also a little indirectly in electricity generation. You will see hydro still growing, but basically solar and wind will become the workhorses of the electricity and energy generation, because at the same time we'll electrify the end users, and the electricity share in total final energy rises from about 20% now to about 50% by 2050. And yeah, electrification is a way that will allow a big penetration of renewable energy in the global energy mix. I wanted to show you this because already 2 years ago, the China National Renewable Energy Centers also showed that electrification share are key to decarbonization. And basically in their Renewable Energy Outlook 2019, they show that the three pillars of going to a decarbonized world are green power supply, energy efficiency, and electrification. And here the growth of the share of electricity in final energy demand for buildings, where it's already 30%, going to almost 60%, 28% for industry, going to over 50%, and finally transport, now very low rate of electrification, going to 40% basically. This is for China, but it goes exactly in the same direction of the IEA global proposition. Let me say some words on green hydrogen, because it has become a very hyped topic for good and overhyped reasons, I would say. What are we going to do with green hydrogen? Firstly, we're going to green ammonia and methanol for their current industrial uses. We're also going to green the hydrogen that we use in refineries to upgrade and clean fuels. But of course, refineries will use less and less fossil fuels, so this is going down and not up. A big emerging area for using green hydrogen will be steel making, in particular because we can do direct iron reduction with hydrogen, and this will be very important in terms, in absolute amounts of hydrogen demand. But I'm sure Johannes Schenk will say more on that. We'll use ammonia, which is another form of hydrogen, which is hydrogen with nitrogen as a shipping fuel. And this is now ongoing already with the manufacturers of maritime engines and the shipbuilders, etc. It's ongoing. We use methanol and synthetic hydrocarbons as electrofuels, or I would say electro feedstocks, a feedstock for the chemical industry, which is often based on carbon, and also fuel for aviation in particular, because the aviation really needs the energy density of the hydrocarbons. So we need to replace kerosene with e-kerosene if we are to decarbonize aviation. Of course, these products, alcohols and hydrocarbons, they do contain carbon atoms, so they will only be really sustainable if not only the electricity to make the hydrogen is green, but also if the carbon is taken out from the air. And there are two ways from taking the carbon from the air. One is mechanical, if I can say that, direct air capture. The other is through the biomass, and we can combine the production of electrofuels or feedstock with that of biofuels or biofeedstock, by the way, because there is much more carbon than hydrogen and energy in the biomass than there is in the fuels and the hydrocarbons we use. And you see that when you do biofuels today, you have a surplus of carbon, and the big ethanol plants are very important sources of concentrated CO2. But if we have sufficient green hydrogen, we can combine this hydrogen with this CO2 and produce more fuels. And these fuels are in part biofuels and in part electrofuels. We can also use the oxygen to help to the conversion of the biomass feedstock. And this, I think, is a very important area. I'm pleased to note that these schemes that I've been using since 2016 have been drafted by Ilka Ahanula, who is my successor at the IEA. And then we have the use of hydrogen and sometimes ammonia as storable and shippable fuels in the power systems. Hydrogen, when we can store in the power system for the achieving, completing the decarbonization of the power system, we can use some hydrogen in fuel cells or turbines. In some cases where we don't have the geological option of saline cavities to store hydrogen, maybe we'll use ammonia instead. And also because ammonia is easier to transport from on ships, for example, from one area to another, we can prefer to use ammonia instead of hydrogen. So we'll use both in power systems to really achieve the 100% decarbonization of them. And we have the hydrogen and power-to-X fuel, which can be e-gasoline, etc. I believe they will find some markets, small markets in ground transport, where they are hampered by low efficiency. All the conversion means that this is much less efficient than using electricity directly. And so my belief is that we'll see lots of electrification, direct electrification, and in some cases, the use of either hydrogen or power-to-X fuel. Power-to-X fuel are even less efficient than direct hydrogen use, but they can be drop-in fuels in existing engines, and the overall cost may be different. They can also be produced in areas with much better resources and transported easily, which is not the case with hydrogen. So there is a trade-off in the advantages and inconvenience of both areas. And then the hydrogen and power-to-X fuel, I think, are really too heavily penalized by low efficiency for delivering space heating and low temperature industrial heat. If you compare with heat pumps, the difference is staggering. With hydrogen, you have at best 50% efficiency from electricity to heat delivered, while with heat pumps, you can have an apparent 300% efficiency, a coefficient of performance of 3, which means a gap of 6 times the efficiency in transporting the green electricity to deliver heat in buildings. And therefore, I think there is no real room for hydrogen and these fuels in buildings. Let's see what the IEA tells us about the role of hydrogen in the road to a net zero emission by 2050. In shipping, it's mostly ammonia, as I just said. They see some in road transport. I'm a bit skeptical on that. Aviation, that would be synthetic fuel, e-kerosene. And then, of course, a lot of consumption in chemicals. And finally, an important role for hydrogen in iron and steel. Where will it come from? Will represent a six-fold jump in the amount of hydrogen. It has to be green. Today, it's not green. It's an industrial gas with lots of associated CO2 emissions. It will be decarbonized in two ways. One is with carbon capture and storage. That's sometimes called blue hydrogen. And it will be also with water electrolysis run on renewable electricity, mostly renewable electricity, maybe some nuclear here and there. And that is called green hydrogen. I'm not responsible for the choice of colors here. And you see there is a role certainly for blue hydrogen, but over time, hydrogen will certainly dominate and be a way to complete the electrification of the end users. Industry now represents, of course, a major issue for climate change. See how it was seen in the IEA 5 years ago in this 2-degree scenario, which is less ambitious, of course, than the net zero roadmap we now have. And you see that basically in the power sector, we would have achieved decarbonization, even with perhaps some a little negative emissions, but transport here and industry would have remained the big sectors with huge emissions. And so, because the assumption was that it's too difficult to decarbonize, I think we have made progress in identifying the ways of doing that. And in this industry, cement making, steel making, and chemicals are the three areas responsible for the bulk of the industrial emissions. And the reason for that is that it's not only energy related, but it's also process related. Reduction of iron ores emits CO2. The manufacturing of cement also is responsible for process emissions of CO2, and therefore it's not only an energy issue, it's more complex than that. Still, the industrial heat is very important. It's 25% of global final energy demand. It's 3/4 of the energy demand of the industry. And this process heat is, at least half of it is high temperature heat. So it's a bit more difficult or it appears as being a little more difficult to fully decarbonize. Just a word on cement. As I said, hydrogen will play a major role. There is another technology, electrowinning, which is less mature, but which is promising, but it's not ready on time to achieve decarbonization by 2050 or to play a big role in that. So we believe that hydrogen will play the major role. You see here that there are two ways of making steel. You have the blast furnace with the coke, and that's the oxygen route, which is very emitting of CO2. And then you have the direct reduction, which already exists, of course, which is made with syngas extracted from natural gas. So it also has a significant CO2 content. And then it goes together with the scrap in the melting of the arc furnaces. The idea here is to replace progressively the mix of hydrogen and other gases, in particular carbon monoxide, with pure hydrogen in order to achieve full decarbonization or almost full decarbonization of the cement making. Now, with respect to high temperature heat, it's often said that it doesn't work with electricity. You see here a quote by Bill Gates in his very recent book, and this passionate of technologies say, well, when we're looking at temperatures in the thousands of degrees, electricity isn't an economical option. Even the IEA in this report has some doubts. Hydrogen and CCUS technologies together contribute around 50% of the emission reductions in heavy industry. I'm not sure. The IEA says these technologies enable the provision of large amounts of high temperature heat, which in many cases cannot be easily provided by electricity with current technology, and help reduce the emissions, etc. I'm not convinced. And first of all, 25% of steel already comes from electric arc or induction furnaces, which proves that electricity can achieve very high temperatures, in fact, higher than you get with combustion, even of hydrogen and oxygen. And you see here several options. The first is heat pumps. Of course, that's for low temperature. Then you have the electric furnaces, and you have a bunch of electromagnetic technologies that go even much higher. And of course, you have the renewable hydrogen. So direct electrification of industry can take several forms. The first, of course, is heat pumps and also mechanical vapor recompression. But then you have all these electromagnetic technologies for heating, hardening, melting. You have the electric arc heating, the induction, the dielectric heating, like your microwave. You have direct resistance heating, electron beam heating, etc. And of course, you can simply use cheap resistance in boilers or furnaces, taking advantage of cheap surplus power when available. So you can start doing a number of things in parallel with still using some fossil fuels, but shifting to electricity when it's cheap enough. I believe that heat storage can help extend these concepts in a major way. So they are very efficient and can deliver heat at all temperature levels, contrary to what's often said. Let me add a few facts. It's so much more efficient because it targets heat more precisely, that this greater energy efficiency may compensate for higher costs. This was important when the costs were high, but we know now that we'll have a lot of cheap electricity thanks to renewables. So it's not even a concern anymore. It improves most products and working conditions because of the efficiency. The electrification of industrial heat can eliminate diluted CO2 fluxes, facilitating the capture of process emissions in cement making, but also, for example, think of natural gas reforming, where you have, you can, if you electrify the reforming, you reduce the gas consumption, and you end up with just a concentrated CO2 fluxes, which is much easier to capture. So this opens a lot of new avenue. Another use of electricity is the pyrolysis of natural gas, the so-called turquoise hydrogen, with no CO2 formation, but solid carbon as a byproduct. And here you see that you're saving times and you're saving lots of energy in variety of areas, industrial areas. The gain of time is also very important from an industry perspective, I believe. Another hint on what the Chinese have been thinking, they showed that if you electrify the industry, well, you reduce the peak valley ratio, because it's mostly constant demand, so it reduces the variability of the demand, and this may help integrating more renewables. But I will say more on this because it also can be very flexible and do much more than that to help integrate more renewables in the mix. Another important point is that storage at end-use level is often less costly than electricity storage. One example is cold storage in air conditioning systems, because you have several hours delay between the time when the sun sets and the temperature cools in the buildings. So you need to continue cooling the buildings in the early night. You can do that with chilled water, ice, etc. You have here another example in water supply distribution systems that was proposed already a few years ago. So demand response is important and can integrate a number of forms of storage, different sort of storage. And here is one very important sort of storage, which is the compact high temperature heat storage, which today is a missing link, but it's coming. Of course, some industry proceed in batches, and they are often already managed to use cheap electricity at appropriate times. But many processes require continuous high temperature heat supply. Heat storage is needed to benefit from cheap renewable power, wind or solar, and deliver continuous high temperature heat to industries. It's this missing link that should be considered very, very closely now. Think of all what we could do if we had that. We could have steam for processes or power, heat in the superheated air or another gas for drying, calcining, etc. We can do, of course, combined heat and power with that, turning so the viable electricity of solar and wind into continuous electricity, steam, heat, whatever. The current heat storage options are limited and storage options by and large. Batteries have high return efficiency but high costs except for short duration storage. Hydrogen, it's the opposite. Low return efficiency, storage costs very high at end use level, low only in underground caverns, saline cavity, only justified for very long duration like seasonal storage. And then we have a bunch of emerging heat storage solutions, but today they are still limited in temperature with concrete, molten salt, volcanic rocks as storage medium, limited to about 650 Celsius degrees. Some are trying aluminum or steel as storage medium, up to 1000 degrees. They are slow in charging and discharging because both charging and discharging is convective, and they are complex and costly with high temperature fluids, pumps, heat exchangers. All this is complicated and costly. You need lots of materials to doing that. I think what the industry needs is a storage that can work at 1500 degrees or more, that is efficient, fast, and simple, durable, compact, and cheap enough. And I think it's coming. It's coming. We'll hear about it in the coming months, maybe a 1 year time, and you will see that appearing on the market. Electrifying end users help integrate more viable renewable. And I'd like to spend just a minute on this. Here is a modeling of the electricity in South Africa by colleagues from Enertrag, and they have thought of making all solar and wind. And here is what this becomes. This is the electrical need, and this is the solar production, the wind production. And you see that you have a number of residual load and also of curtailment. But the residual load is relatively important and requires some thermal power plants and some fuel. So it's hard to have all this amount of low carbon fuel. Now, if you use that electricity, more electricity to produce hydrogen and to deliver heat and store heat in industry in particular, not only, also buildings, the proportion can be discussed here. But the important point is that you can have much higher amounts of solar and wind that is financed, that is profitable because the electricity is used. It's not surplus electricity, it's electricity, someone is paying for that. But all these electrolyzers or heat used can be stored or can be slowed down when at times of high demand or low production. And this allows to keep the electricity when it's in short supply or high demand for the ordinary need of the electric grid and not for hydrogen production and production. which you will produce when you have a lot of renewables and relatively low demand. And this allows to reduce considerably the residual load and make the integration of viable renewables much, much easier. Even before you start considering using some of this hydrogen to put back in the power system in a hydrogen turbine, which you will need to do at the end to go to 100% no carbon electricity, the production and the sector coupling of the electric system to the industry, to the buildings, to the transport will help integrate a lot more renewable. And I insist on that because it's not always well understood, but it's very, very important, I believe. Let me sum up how to avoid a climate disaster, to take the title of Bill Gates' book. I think we agree, I agree with Bill Gates on the most important features: generalize carbon-free electricity generation, improve energy and material efficiency, electrify almost everything, buildings with heat pumps, transports with Li-ion batteries, industries with electromagnetic technologies, and efficient, cheap, fast, and compact high-temperature heat storage. Use hydrogen when you cannot proceed otherwise, and only when you cannot proceed otherwise. For chemicals, steel making, as fuels for ships and planes, long duration energy storage, and also energy trade from areas with bountiful renewable resources to areas with high energy demand density. On this, let me just add that hydrogen is unlikely to be massively traded as such, rather will be traded as finished or semi-finished feedstock and fuels. There is no time to lose. This is my very final slide. The key milestone, the pathway to net zero. I think you will look at it clearly, or in the reports, or in this slide when you get the PDF. Let me just mention three. Sorry. Right now, no new unabated coal plants approved for development, no new oil and gas fields approved for development. That was very important. No new coal mines and mine extensions. So that's right now, that has shocked the world, I must say. And just look at these yellow ones here. Most new clean technologies in heavy industry demonstrated at scale by 2030. And that's, I think, is very important. It means what we have to do in the next 10 years. Thank you very much for your attention. I hope it wasn't too long.
Thank you, Cedric, for this thought-provoking, I have to say, talk, and really set the scene quite well to what follows with the next talks. So please hang around for the other talks, and we'll have a panel discussion. I know I have lots of questions for you as well, and there's some online. Our next speaker is Badr Salim. He's from Ma'aden here in the Kingdom of Saudi Arabia. He will tell us about decarbonizing mineral industry here in the kingdom, in particular Ma'aden's experience. He's a manager of Renewable Energy project at Ma'aden. He's an electrical engineer by training. And please go ahead and load the presentation. He got his postgraduate certificate in engineering project management from the UK in 2000. He has 30 years experience in managing projects in the power and petrochemical and mining industry, and has many certificates. He has been quite active in a lot of areas. I had the pleasure actually to interact with Badr in the last 2 days while visiting KAUST in here, and looking forward for his contribution.
Thank you, Dr. Bassam, for that introduction, and thank you for inviting me to this event. So mainly we'll go through our experience, energy, power production, power for all mines. Most of Ma'aden mines at remote area, there is no access to gas, no access to electricity grid. So we depend heavily in diesel power generation. We didn't have a problem at the beginning because the diesel was subsidized by the government, and diesel price, fairly low price. but by 2018, the government will start removing the diesel subsidies from all fuel. And by 2025, it will be international price. So we have to find other solution to minimize the risk from Ma'aden for increasing the cost of electricity for our mines. And we found a good solution to introduce solar and wind with a small amount of batteries to reduce the consumption of diesel. By reducing the amount of diesel, automatically you reduce the CO2 emission. Here you will find what is the existing power or electric tariff for industrial, which is 18 halla per kilowatt hour, still a very, very good price. For commercial, it's 30 halla per kilowatt hour, and that for Ma'aden headquarter, it's almost double the industrial tariff for all Ma'aden plants. For power factor, it was 0.9, and now last month it's increased from 0.9 to 0.95. If you don't reach to that amount, you will pay a penalty 5 halla per kilowatt. This is the main thing to take in consideration, but that one, as of today, but it will, after the government remove the subsidy from the fuel, the tariff will increase. This is a fiscal balance program for 2030 vision for Saudi Arabia. It's clear here. The diesel price, starting from 2018, will increase gradually, and it will be international price by 2025. We heavily depend for power generation in diesel. Also for gas, it will increase. For natural gas, it will increase, but with a ceiling. It's not. It will not be international price. If the government remove the subsidies from gas and diesel, the electricity tariff also will be increased starting from 2018 to 2025. And this shows what will be the electric tariff by 2025. We have some power plants. We have some Saudi electrical company generate power from diesel power plants and some from natural gas. The blue line represents what will be the price if it's only gas power plants. The red line, what will be the tariff if it's only diesel power plant. By combination, it will be that dotted line. And the diesel price for the international, it will reach almost 200 halala per liter, which is almost 53 cents per liter. But until now, we are now in mid of 2021, the diesel price not changed. We calculate what will be the cost for Ma'aden if we don't move, if we don't introduce the renewable energy. The red dotted line shows that if the diesel price remain the same, this will be the cost for Ma'aden per year. And the black line shows if we didn't do anything, just we accept increasing the diesel fuel without trying to minimize the diesel consumption. So there is a huge gap between existing and the future cost. You will see sometimes it just goes down. Even if here, starting from 2025, it's international price. The reason for that one, it's a gold mines, it's a short life. So some mines will be closed, another mines will be started. That's why you will not find straight line. The green dotted line will show what will be the cost of Ma'aden paying in diesel after reducing the diesel consumption by introducing renewable energy, which is mainly solar PV and wind, in addition to battery, small battery. In Saudi Arabia, we have good amount of GHI, the global horizontal irradiance. For example, if you have 1 square meter of solar panel, it will generate 2,400 kilowatt per year. Kilowatt hour, yes. And if you compare it, for example, with Germany, the same square meter will generate only 900 kilowatt hour per year. So we almost triple the amount of Germany for solar. And the solar is proven technology, is now more than 300 gigawatt installed capacity. And the main reason to introduce the renewable energy just to reduce the consumption. Just to reduce the consumption of diesel. We did a lot of simulation. What is the best levelized cost of electricity by introducing what is the size of PV, what is the size of solar, what is the size of batteries. And we found that for 3 megawatt and below, we will use only polycrystalline modules with fixed mounting. And for greater than 3 megawatt, bifacial, because we'll receive it from both directions, and with single axis. We will not depend 100% in renewable energy, because it's depend the PV will depend in solar, wind turbine will depend in wind. So we make it in combination with the diesel engine and batteries, the battery storage. Battery storage will not size it for the whole night, just for 1 or 2 hours to avoid if there is any shutdown in the renewable energy, it will give enough time to start up the generator. This is the assumption for our simulation feasibility study. The power available 100%, 24/7. And in addition, we will have 15% installed capacity as a redundant, 20% spinning reserve in the running engine, because if there is any interruption in the renewable energy, it will be covered automatically by the spinning reserve. Exchange rate, $1 equal 3.75 Saudi Riyal. I mean, 100 cent equal 375 halala. We did the feasibility study for 14 mines, some of them connected to grid, and most of them isolated, depend 100% in diesel power plant. And you can see from here the levelized cost of electricity will be improved. But for some plants, which is, for example, very small, doesn't work to install that amount, because, for example, in Ghazal, it's 0.2 megawatt. So it doesn't work to make renewable energy. So it will remain. And here you will find the power supply recommendation, what we recommend. For Mahd, for example, we recommend to connect to the grid without installing renewable energy, just because the remaining life only 3 years. And PV panels guaranteed for 25 years. So what you will do with the remaining life? So if you connect to the grid, it is the best option at that situation. We make a lot of scenarios for each mine. Connect to the grid, connect to the grid with PV, connect to the grid with the ultimate PV size. And here you will see the regulation as of today. If you are connected to the grid, the maximum PV size, 2 megawatt. You cannot increase more than 2 megawatt. We hear that this will be changed soon, and they will allow for wheeling power, and they will allow for self-generation, and they will increase also for the renewable energy. But still, we didn't have that regulation published. This is just what we did for each mine. And here you will see, for example, we have 2 mines, which is Arjum and Mansoura Masarra. This is gold mines. It's a new mine. And the remaining life, 12 years. This is the normal life for gold. For Jalamid is phosphate. Mine life, 25 years plus. Adwehi, Jabal Side is copper mine. Also, the mine life is 10. Adwehi, the remaining 5 years. So this is, you would think twice. Does it worth to add renewable energy to it, or remain and pay the diesel price for the remaining life, which is only remaining 5 years? Mahd, it's only remaining 3 years. So we will not add any renewable energy to that one. Al-Amar connected to the grid will add to it as of today 2 megawatt, because this is the maximum we can install as per the regulation. When they revised, we will increase the capacity. Bulga, B'itha, it's a bauxite mine, and the life of that mine, 25 years plus. Hassou, it's a gold mine, and this is this is also excellent location for wind and PV, and it is in center of 5 mines around it. So we can build renewable energy power plant and connect to the mines nearby. This is the Ma'adin headquarters in Riyadh. We have a good size of parking lot. We are not utilizing that one. If we replace that tent by PV panels and connect it after the metering, it will reduce the invoice minimum 60%, because when we calculate it, it can generate minimum 1 megawatt. And that office occupied during the day. So it will be excellent for that one to to change that one to PV panels, reduce the tariff. And Ras Al Khair, it's different story. For example, this is alumina refinery, steam power plant, designed for crude oil, HFO, and now we have a gas. The exhaust, we can reduce it. Exhaust temperature, it was designed for 150 degrees. And because we changed the fuel, we can reduce it to 110. So we have almost 40 degrees. We can utilize that, save that power. At the same time, we have here future plant, we can call it. We can use CSP and generate steam and shut down that one. This is the location for a souk, which we will make renewable energy power plant, wind and solar. And here we will have Mansoura Masarra, Ad-Duwayhi, Arjum. So there is a lot of mines nearby. We can supply with that one. At the same time, we'll connect to the grid. This is the problem now with the regulation, with ICRA. ICRA is the regulator for power supply. If here, now, as of today, if you take the power from other than the national grid, which is SEC, Saudi Electrical Company, you have to pay all of these fees, regardless. Now, because there is no regulation for renewable energy power plant. So hopefully they will change it for renewable energy power plant. There is no fees, and we can wheel it to other locations. So this is the souk location, the centralized PV wind hybrid. We will power Arjum, Ad-Duwayhi, As-Souk, Mansoura Masarra, and also we can wheel it to the other locations. At the same time, we have another excellent location for wind and PV at Wa'd al-Shamal, North Promise. It's near Jordanian border. We have Jalamid and Wa'd al-Shamal, big power consumer. We can build PV and wind power plant and connect it there. And this is the liberalized cost of electricity for both locations, Jalamid and As-Souk. For Jalamid, on 4.6 cents, and for As-Souk, 4.25 cents per kilowatt hour. At the same time, we have a program to minimize or increase the power efficiency. So we go to 2 companies to make audit for power and Ma'adin, and complete program, energy conservation program, including PV. And we have a guarantee that they will reduce the power by 10 to 15%. And we said, okay, they will finance it, they will implement it, they will purchase all things, and we will pay them from the saving. That will remove the risk from Ma'adin. So, and this is the end of that presentation. And thank you.
Thank you, Mr. Abdel for this interesting talk. Saudi Arabia has great potential, a good solar resource, of course, that it can capitalize on, and a combination of solar and wind in the north, which is actually quite good. We're running a little bit of late, but hopefully we'll catch it up in the discussion. But I'd like to now introduce Professor Gusnathan from the University of Adelaide. He is the director of the Centre for Energy Technology at the University of Adelaide in Australia. I have worked with Gus since 1998 until last February when I moved here to KAUST. and he's highly accomplished and one of the world experts in decarbonizing heavy industries for many years. Started his career in the cement industry, where he developed the gyrotherm burner that it was commercialized by FCT. He worked with him in designing burners and so on, so he's well versed with the industry. He won many awards over the years, and he published hundreds of papers and given a lot of invited talks. Without further ado, I'd like to ask Gus to speak about pathways for low carbon alumina production. Gus, the floor is yours.
Thank you very much, Bassam, for the kind words and also for the invitation. It's a great opportunity to be part of this great panel and a really good meeting. You'll notice also that I have acknowledged Bassam in this presentation because he's played a contribution to the earlier parts of this program that I'll talk about. And of course, I'm also part of a large team, and I'd like to acknowledge the other co-authors who are listed here. Just have to get this to move forward. Okay, so a few words about alumina first of all. Alumina is typically produced in very large industrial plants, and this is a size of one of the industrial plants by Alcoa, one of the major producers. This is one of the Western Australian refineries. The material itself is small powder, typically the order of somewhere less than 100 micron, as shown here. And alumina is an aluminium oxide, which is an intermediate in the aluminium production process, made by high temperature processing with combustion. But after this, it goes into the electric arc furnace where it's converted into aluminium. This gives you the indication of the global production rate. And out of this, about half of the world's production roughly is produced in China. Australia is one of the largest exporters, but there's also a number of other countries. The greenhouse intensity is about 0.7 tonnes of CO2 per tonne of alumina. And there currently isn't a commercial technology for net zero that's been demonstrated, which is why we are working on it. Just trying to get this to... So in Australia, alumina is the biggest consumer of industrial energy, as shown in this figure here. And I understand it's also of interest to Saudi Arabia, which is also one reason why, I guess, why it's included in this meeting. So this is in Australia the biggest source of industrial process heat, and you'll see from this figure that about half of the energy is in the low temperature range, around about 250 or so degrees, and about half is in about 1,000 degrees C. And this is the two stages of the process. The process has been under progressive improvement over many years, and now it is quite an efficient process. This is actually a figure from a former alumni of our university, Alessio Scarcella, who's currently the senior technical specialist in alumina in Autotech. And you'll see that the efficiency now is approaching the theoretical limit of the current industrial process. Compared with what would be done in an ideal process, there's still a little way to go. And I'll say a bit more about some of those opportunities later on in the presentation. There are a wide range of potential pathways to produce the heat that's needed for these processes. The low temperature route actually requires steam, which could potentially be provided by concentrating solar thermal. We've done some analysis on that, but I'm not going to talk about that so much in today's talk. So solar thermal is both the commercial and the emerging. Hydrogen is potentially commercially available and a relatively easy fuel to burn. So it's easier to retrofit, but it hasn't yet been proven in this industry. So there's still, and the cost, of course, is still unknown in the current stage because of the commercial cost of hydrogen in a green hydrogen in a variable supply is not yet fully known and demonstrated. But of course, as Cedric so well put the early stage, these costs are falling. So these are the drivers. Same with electrification. There are a lot of electrification options. We'll say a few words about this, especially because of the interest as per Cedric's introductory talks. And you'll see that although it's potentially available, it's not necessarily straightforward in the short term as to how to do that transition. Carbon capture and storage is also a potential option, but I'm not going to talk about that one today. So a few words about the actual process itself. So alumina comes in as alumina trihydrate. This is what bauxite is, and it contains impurities. There's a little bit of CO2 from the mine process itself. It then goes through the low temperature stage, which depending on how many impurities depends on what this temperature is, but it's in the order of 240 degrees Celsius. And this is provided, this heat is provided from steam. And this steam currently is typically done from a combined heat and power system, which is relatively efficient because the heat and power both are useful. And then the steam after that is vented at around about 100 degrees C. This the digestion process also removes the impurities from the bauxite, and then the alumina trihydrate without the impurities then goes into the high temperature process for with the calcination, and the calcination term actually is the release of a gas from a solid material that's heated. So importantly, here you'll see that the alumina trihydrate contains OH, which converts when it goes to alumina oxide, releases steam. So this steam hypothetically could be used to replace some of the steam which currently comes through here. If that could be achieved, there would be a significant gain in efficiency in the process. Currently, of course, this steam is diluted in CO2 and also nitrogen, which is why it's difficult to recover. But this is an opportunity. Of course, also this process is endothermic. It requires energy. This means although this reaction runs at 1,000 degrees, if you're going to provide it from another source, such as electricity, you would need to have a higher temperature than that to achieve the net energy. And this is one of the challenges that I'll say about with the direct process of converting it. I'll return to that later. But first of all, just to show you some of these energy flows, the energy requirement and also the CO2 from the mining is quite low. But in the digestion stage, you'll see there's some energy required to make the steam. But interestingly, that fairly matches the amount of steam that is produced from this calcination step, which is the driver to potentially try and recover that. Ideally, you'd like to return this into here. The other stages is a bit of energy required for the lime, which is in the digestion process. And while the energy is relatively low, the CO2 is significant because the CO2 also comes from the calcination of the limestone. And then there are other losses that I won't refer to in this process. So returning to the actual details of what this calcination step looks like here, you see this is the high temperature part of the process. So the gibbsite, which comes from the mine or after it's been purified, it goes into firstly a direct heat exchanger, which is basically a cyclone where the hot gases from the flue gases are used to preheat the material. Actually, it's several stages of these heaters, but it's shown here as just one for a simplified component. This is actually some of the water is released in this first stage of heating before it goes into the high temperature furnace. Then both the material and the hot gases go into the holding vessel to complete the conversion to the right quality of alumina for going into the next stage of the arc furnace. Then some of the energy is recovered in the coolers, which then is the air then goes into the preheater and into this furnace. But importantly, then the steam that comes from this process from the calcination step is then diluted in the nitrogen and the CO2, which is the challenge for its recovery and which is why it hasn't yet been recovered to date. So one of the first step I'll show you some of the quick analysis that we've done is on this electrification option, which Cedric was right to highlight the potential value. Certainly industry is very interested in the electrification option as a pathway to low carbon for all the reasons that Cedric illustrated. So the first, we have done a fairly detailed process analysis of some of the constraints and opportunities and also limitations of what would be required. Firstly, it's desirable if we can retrofit a process, and so we analysed the case where the hot air coming from the aluminas was first of all heated, and starting with the system that is commercially available at large scale, which is resistive heating. And as I mentioned before, because the alumina calcination reaction is endothermic, that means if you want to achieve 950 in here, you need to achieve a lot higher temperature in the air to still balance that temperature and provide the enthalpy for the reaction. To analyze that process, and I'm not going to go into the details, but I'll just show a little bit of the few elements. The current, if you're going to use current technology with resistive heating, then up to, in this case, a roughly say 40% of that energy can be achieved with 1500 degrees C. This can be done quite efficiently. On the other hand, if you want to go to the temperature that's needed to do the full conversion, you need to go to very much higher temperature. You need to get to about 2400 C, and the technology is not available to achieve those temperatures commercially at the moment at this scale. But even if it was, also the efficiency of that is lower. So the CapEx and OpEx, I'm not going to go into those details. We calculated NPV as per the normal routes. There's a lot of details here that again I won't go into, but just to highlight again in this bit here that that the efficiency of a heater at that high temperature is only about 50%, whereas it's 92% for the commercially available system. Going through the CapEx and OpEx, again, just cutting to the final values here. Because of that change in efficiency, this is the total energy required if you're going to do more and more electrification. So you'll see at any one point to meet that total demand, you've got a mix of fuel in this case in this blue line, and the electrical energy in this dashed line. And this is a nonlinear curve because of the change in efficiency with temperature. And so you'll see that currently, with the temperature that's available with commercially available resistive heating, you could achieve about 1450 degrees C. So the electrification would supply just under half of the energy. Now, one of the reasons for that is because you need to have excess air in the system to transport the alumina through this current process. If you develop a new technology, of course, you may be able to change that ratio somewhat, but these are the constraints of electrifying a current process. So that shows you that with current technology, electrifying a current process, we'd be limited to just under half of the energy that could be supplied electrically. And then we also need to compare that with the cost of electricity. And so this is depending on the price of gas in US dollars per kilojoule, and in the US, you're somewhere around $4 a gigajoule. In Australia, it's probably around 6.5 or something like that. It depends where you are in the world. And the world average electricity cost is much higher than that, so currently wouldn't make sense with the world average cost. The Australian cost is also currently would mean that wouldn't be economic, just on economic terms alone, even though this does include some CO2 price of $100 a tonne in this analysis. Of course, it may be viable for short periods of time when the electricity costs are lower than the average, but then you would achieve a less than that 50% share. So there are some challenges, but nevertheless, there are also some opportunities. I'm now going to say a little bit about the opportunities to try and recover that steam. So ideally, of course, if instead of doing the calcination in air and combustion, if you do the whole lot in steam, this is a desirable approach. What you would do is potentially you would put steam into this system that heats steam, so there's now no air in the system. You do all of the calcination using an external low carbon heat, and then the only product is then steam, which could then go to the digesters, automatically recoverable. Now, this concept is not entirely new. In fact, Alcoa themselves, Alcoa has done some work on this in the past with a process they called a two-stage calcination step, where there was in this case, only the low temperature part of the calcination step at about 350 C was done under pressure and entirely in steam, allowing that to be recovered. Then this was transferred into a high temperature process. Now, this system was never commercialized, but it was demonstrated at pilot scale, and part of the number of commercial reasons as to why it wasn't continued, including this being developed at the time of the GFC, and there were some challenges with the high pressure stage of this process. Nevertheless, it shows the interest. I will present you a few of the results that we've done to better understand what the kinetics of running this process in steam are and what the impact on the material itself is. So we run a whole series of experiments here, calcining material in steam and then looking in detail at the properties. What you see here, this is the specific surface area of the alumina product as a function of the loss on ignition, which is the inverse of completeness of conversion. So if you get to zero, this means you have complete alumina oxide, and they don't quite go to a complete alumina oxide in an industrial process, but the smelter grade alumina, this is the what goes to the commercial plant with current technology. And what you'll see, importantly, is that running this process in steam actually achieves, for the same level of LOI, achieves a higher surface area, which is actually an improvement in product quality. The other thing to notice is that this is achieved at a temperature of only between 750 and 850 degrees Celsius. So it's lower than the 1,000 degrees of the current commercial process, which could also result in a greater efficiency in the process. So I'm not going to go into the full details of beyond that, but I will just conclude because of time. The main points are that electrification of alumina calcination with current technology does have some constraints. The maximum contribution will be limited to about 45% with current resistive heating technology. And also to achieve that would require electricity prices well below half of the current world average, even though you could potentially achieve it with lowering emissions. And of course, prices may come down in the future, etc. But we're talking about what can be done today with these particular conclusions. Potentially, calcination in steam could offer many potential advantages, and some of these could potentially increase this viability of going to these lower carbon options, including greater efficiency, improved product quality, potential to go to a lower temperature, which would further increase the efficiency. But further development of the technology is needed to implement this, which is also in line with Cedric's target of 2030 by demonstrating these new technologies. We actually also are working on one of these other technologies and have provisional patents on that, but I can't go to that today. But very soon we will be publishing this material, and we'll be very happy to talk about it at that stage. But in the meantime, we're very happy to talk about the principles and other opportunities in the discussion. But thank you for now.
Thank you, Gus, for the interesting talk on alumina, which is one of the major contributors of CO2. Maybe we should have titled this session "To Electrify or Not to Electrify," but I'm really looking forward to the discussion about that with Cedric and Gus later on. So we covered alumina, and cement is obviously one of the major contributors. Our next speaker is Anne de Coquillard. She is the managing director and co-founder of partners at Cementis. Sorry. So Anne had quite a long career, 25 years in a lot of area related to cement. She worked on to many of the major companies in the cement industry. She managed lots of projects on sustainability. In fact, she has a master's in sustainability from the University of Harvard. And now she sort of have her own company looking at being advisor to many countries around the world and on how to decarbonize cement. Her title is Pathways to Decarbonizing Cement Manufacturing, and I asked her to also look at Saudi Arabia, because this is a project I'm working on, looking at what are the pathways in here, and Anne is one of our consultants. So please, Anne.
Thank you. How do I get my presentation? It's here. Okay, do you hear me? Yes. Hello. So I'm here to look at the cement manufacturing, another heavy industry, polluting, emitting a lot of CO2. Let's look at the figures. Worldwide, we produce around 4 billion tons of cement. A bit more than half is produced in China. You have to know that China increased a lot its cement manufacturing. We are now at the top. It should decrease in the coming years, but majority is coming from China. Saudi, with its production of 50 million tons, is around 1.2% of worldwide production. But we have to know also that cement is responsible for 7% of the worldwide GHG emissions, which is not negligible. Where does the CO2 come from? Why there is CO2 emission from the cement industry? In fact, most of it comes from the process emissions. So the clinkerization, if I can say that. 40% comes from the thermal, so the fuel. And a bit less than 10% is more electricity, transport inside the plant because of grinding, cooling, and quarrying. In Saudi, cement represents 8% of the national GHG emissions. You have to know, in terms of the CO2 of the industrial process, cement represents 52%. This is the process emission, and 3% for the fuel. There are 4 levers in the cement industry to reduce the CO2 emissions, and I've put there in terms of somehow short, medium term, and longer term. Longer term, I mean after 2030, and I will explain it. So the first one is the improve of energy efficiency, reduction of clinker content in the cement, the clinker to cement ratio, the alternative fuel, and the use of carbon capture, utilization, and storage. Let's go through them. The first one, improve of energy efficiency. I think the cement industry did a very good job for all those years. We don't find worldwide, really maybe in Europe, the oldest one, wet kilns or semi-wet kilns. When you look at the megajoule per ton of clinker they needed to produce, so all those wet kilns do not exist anymore here in Saudi. We are more in terms of 4 or 5 stage cyclone, which is this better. So there might be some options here in order to increase this energy efficiency, but the capex versus the reduction of CO2 might be a bit challenging. But in Europe, we could easily gain some CO2 by replacing the wet kilns. They are still existing in Europe, or the semi-wet kilns. The second one, and which is the biggest lever we could act, is reducing clinker into cement. We have to know that here in Saudi, most of the cement sold and produced is OPC. OPC is 95% of clinker, 5% of gypsum. According to EIA, clinker cement ratio in 2020 was 71% worldwide average. We should reach 57% by 2050, which is a big reduction. which means that we need to add alternative raw material. We need to use the cementitious product in order to replace clinker. In Saudi, we have limestone, pozzolana, and probably clay. So let's look into those cementitious material. We have limestone, this is one, but we know the CO2. We have fly ash. This material should disappear very quickly. Slag, the volume would also decrease over the years. The issue with the slag is sometimes the cement industry either cannot access good quality slag or it's not available in the region of the cement plants. Then you have natural pozzolana, which is also difficult to have according to the place you have your plant. And then you have calcined clay, the colonite clay, in fact. I took again this EAA graph 2021 published maybe last month, where we see the possibility of material that the cement industry could use. And we see the fly ash disappearing, the increase of limestone and the increase of kaolinite clay. But what is kaolinite clay finally? It's quite recent. Maybe 5 years ago, EPFL University in Lausanne came up with a new recipe of cement of 50% clinker, 30% calcined clay, special clay. It's a kaolinite clay with minimum 40 to 60% kaolinite content, 15% limestone and 5% gypsum. What is specific to this new formula is that it has the same strength as an OPC, as the same one, the purest cement. So we go from 95% of clinker to 50% clinker. We have similar strengths as OPC, better chlorine and alkali silica resistance. What you only need is a flash calciner or a mini rotary kiln to calcine the clay. And there we are about a capex of 10 million USD, which compared to a new kiln is much, much less. Additionally, we estimated the production cost of this new cement being $7 USD, so less than the normal OPC cement. Then you must say, but where do we find this clay? Okay, that was one of the best pictures we could have, but the kaolinite clay is in yellow. So you have on the left side the topsoil and on the right side the subsoil. For Saudi Arabia, you have some in the western and in the south in subsoil. What is interesting and for the cement worldwide is the kaolinite clay present in Africa, Latin America, and Asia, which are the developing country, which are the country that we will need cement for the coming years because of their infrastructure, their development. Why is it so interesting? We reduce by 39% the CO2 with this cement. Why? Because we add, so the gypsum is the same. We add 15% limestone, which is not cooked, which means no CO2. We add 30% of calcined clay that is heated up at 850 degrees or 850, which means that it's around 250 kg of CO2 per ton of calcined clay. When you compare that to clinker, which is around 850 or 830, it's much, much less. The advantage is that one day, and hopefully very soon, we will be able to calcine clay under renewable energy and electrify the flash calciner. That would turn out then to reduce more the CO2 of this cement. Just a little parenthesis, this cement has just been approved by the new standards of Europe, the EN197, the fifth version. So now we can, according to the EN197, produce such a cement with 50% clinker. Third lever, increase of alternative fuel. We have to know that there is no technical barrier to reaching 100% substitution rate in a cement plant. We have several cases in Europe, Germany, more precisely, where we reached 90%, 95% of waste utilization, and only 5% after maintenance because we had to restart the kiln. But we are reaching 95% of waste utilization and 5% of coal. So it's feasible. The only thing that compared is that in Europe we have the polluters pay principle. It's that when you pollute, when you bring your trash bag, you need to pay. But it doesn't solve everything, because here we only attack the CO2 from the combustion. But we have to know that there is waste and waste. We know that biomass waste has 0 CO2 content, but the other waste has some CO2. If you have coal, which is 96 kg of CO2 per gigajoule, and you use plastic or solvents, you will have a decrease. The challenge here in Saudi is that you earn heavy fuel, which is 77 kg of CO2. And you need to reduce. Or either you go to biomass or you make some mixes with other waste, but it has a CO2 impact. Just as an example, did you know that 1 ton of tires equal 1 ton of coal in terms of energy? But additionally is that in this 1 ton of used tire, we get some raw materials that you don't need to add anymore after in the cement plant, which is iron and aluminium. We have to understand that there is this waste hierarchy there under. And we have to understand that the waste, coal processing and cement industry is not like incineration. We get back the energy content of the waste, but we get also the raw material needed in the cement. That could then, we can reduce, like the example of the tires. Let's look at Saudi. Saudi produces 15 million tons of municipal waste every year. Majority of the collected waste ends up in landfill, and we might have big risk of pollution of groundwater. Only 10 to 15% is recycled, and non-hazardous and hazardous industrial waste also need to be tackled. Where do they end this hazardous waste? We have to know that the cement industry can handle nearly every waste possible, even the most hazardous one. Since we reach a temperature of 1,450 degrees C, which is much higher than any incinerator. So it could be a win-win situation between the municipality having this waste and the cement plants. We just need to work on it. I'm taking again this International Energy Agency, that's the last report that was published, which was really interesting. According to them, the new expected mix for 2050 of the cement industry will be 40% natural gas, which means that we go back to gas. In the beginning, cement industry was in gas. We went to coal after. 35% will be by biomass and renewable waste. This means that the industry has to really enter into how to approach alternative fuel in the cement industry. And especially in Saudi Arabia, where currently the percentage of alternative fuel utilization is nearly 0. They have to begin now. But then we need the support of the government. And the last lever is carbon capture. We have to know that carbon capture, utilization and storage in the cement industry is not a necessity, not an option. We really need that. But it's still on a demonstration stage and prototype. We have 3 different technology to capture CO2, which is direct separation, indirect calcination. This is a LEILAC project financed by the Europe in Belgium. Their TRL is between 6 and 7. You have this oxy-fuel. There, normally there will be a project in Germany under oxy-fuel. Post-combustion capture, and this one will be in Norway, Brevik. This is a bit more advanced, TRL 8. But currently this technology is not economic feasible. We need a CO2 where we pay the CO2 at 40 euro per ton of CO2. So which means that currently in Europe, we don't pay the CO2 above a certain average, but we don't really pay the CO2 per ton of cement produced. But there we would need a CO2 of 40 euro in order to make it feasible. And also another issue is that a lot of cement plants might be very far from any storage capacity of CO2. So that will be challenging in order to do, what do we do with the CO2 that we capture in the cement plants? Then I just wanted briefly to say, it's not only the cement that we have to act down the supply chain. It's stupid to say, I will sell a very low CO2 if the concrete manufacturing is putting more cement in its ready mix than it should be. Or if the building company is putting too much concrete in its building or unadapted concrete. For example, if you put a very high strength concrete on the walls, on the external walls of a house, and you put the same because you don't want to change the mix inside, it's stupid. And architects, maybe they have to stop making pillars too big, or we have to be conscious at all levels, and at the whole supply chain has to work towards that. And as a summary, okay, cement emits huge volume of CO2. The industry really need to act now on the first 3 levers, because the number 4 lever will not be ready before 2030, which means that we have to act now in order to be able to store this CO2 the less possible. We have to also to act through the value chain, and for the Saudi, why not using NEOM as one of the showcase to use a low CO2 cement? That would be really great. Saudi should really beginning to replace OPC by other cement, which means that we have to change the standards, construction codes. We should also look at geological survey for kaolinite clay, increase the use of waste, replacing coal, fuel, whatever, by making it cost effective, which means implementing polluter pay principle. And also really beginning a feasibility of any CCUS project in the kingdom. Thank you.
Thank you. And cement is so important, not just for Saudi Arabia, but obviously for the rest of the world. And this is another one of these industries that we have to do something about. So the last talk in the session before we do our discussion panel, and I'm again sorry a little bit we're running late, is from Johannes Schenk. He started his professional career at what became Brown Metals Technology Austria, in 1990. And then he became a process and research engineer at different iron making technologies, such as Medrex, Corex, and Finmet. He became a general manager and vice president of R&D for the development of the Phoenix process between 92 and 2007. Later, he turned his hand into academia, became a professor of ferrous metallurgy in Leoben, and then and sort of continued his work until 2015. He became the chief scientist officer of the Austrian Meteorological Competence Center, K1 Met GmbH. Johannes published more than 160 papers in lots of journals and conferences, and is a co-inventor of 30 patents. So he will tell us about hydrogen meets future steel making on the road towards CO2 lean steel making in Europe. Johannes, the floor is yours.
Okay, thank you, Mr. Chairman, for your kind introduction. I hope you can all see my slide. Is this?
Yes, we can.
Okay, thank you. Yeah, the chairman already introduced the title. It's about steelmaking in Europe, considering the avoidance of CO2 emissions. The content of my presentation, I would like to start with the current situation of the steel industry in Europe. Then I would like to give the possibilities we determine in Europe about CO2 emissions. There are these three approaches I would like to introduce here, and then I would like to finalize the future steelmaking with hydrogen. In particular, what are the challenges, the opportunities, constraints, what possibilities do we have on the technology side in brief, and how can we integrate such systems which existing systems. Current situation of the steel industry, it's like that. We have now nearly 1.9 billion steel production worldwide. Like in other industries, China is producing more than 50% of the steel. However, Europe as a steel producer, second biggest steel producer worldwide, whereas the European Union represents 74%, for the CIS represents 5.3%, and the remaining Europe 2.1%, which sums up to nearly 50% steel production on the global perspectives from Europe. Which routes for steel production are now available? Yeah, you can see here the possible routes available in industrial scale. It's the production of crude steel. The dominating route integrated based on the iron making technology blast furnace, where you produce hot metal using coal, which is converted to coke. You can charge lumpy ore as lump ore and fine ore in sinter pellets, and then you produce the hot metal in the steel making step, the basic oxygen furnace, to crude steel, and which is further then refined and casted and rolled to get the finished product. The second route, which produces from just we have the scrap recycling route, where you recycle scrap with electric arc furnace. An alternative route for producing crude steel, especially in Saudi Arabia, the common process is the combination and the integrated route of a direct reduction plant with an electric arc furnace. This direct reduction plant is operated with natural gas. And a niche route which is available but represents only nearly 1% of the steel production is the symmetric reduction route. In Europe, dominating route is the blast furnace and electric blast furnace, integrated blast furnace route, and the scrap making route. Already in Europe, more than 50% of the steel is produced via scrap recycling. We have also one installation in the European Union with direct reduction route and electric arc furnace combination. What is the current situation and the development of the CO2 emissions, or say greenhouse gas emissions? You can see here this the trend since the reference year 1999. We in Europe we achieved already 42% CO2 reduction, greenhouse gas reduction to be more precise. And if you compare this with the production of steel, then we can see, yeah, before this crisis, year crisis of 2009, we could see even an increase of the steel production and a decrease of the CO2 emission, which was a quite good trend. But after the recovery of this crisis, the production goes down. However, but no CO2 reduction, significant CO2 reduction could be observed. The reason for that is that now the current processes which are in operating already have a quite high optimization concerning CO2 emissions. That means if we go further for further reduction, which are the baseline is this 80% minus reduction up to 2015, we have to look to breakthrough technologies. Yeah, the background behind Giant is clear. This is the European Commission has defined a roadmap how to reduce the CO2 emission by 2015 to keep target of 5 degrees. And Europe and the European steel industry has in Europe and in the European Union has in principle committed themselves to fulfill this target. So what are the activities in Europe that's going on? And out of, you say, there are several projects and initiatives initiated, and they defined mitigation pathways for CO2 emission in Europe. The first pathway is mainly focused on the existing processes for iron and steel making. It's called the process simplification. The focus is to reduce carbon further by possible options like iron recycling, in particular higher scrap rates is an issue which will be tackled now, although to investigate other savings and recoveries using renewables, also to integrate where possible carbon capture and storage. There are legislatives in Europe which makes it not so, this is not available in every country to store CO2. Initiatives in particular, there are the high SANA process and the top gas recycling blast furnace. They are dedicated to this mitigation pathway. A second mitigation pathway is to the smart carbon and usage. This means to use the carbon, gaseous carbon emissions from existing technologies. We are still on the existing technologies, but then we make a sort of smart usage means that you produce fuels, chemicals. All of these technological options, conversion processes to biological, chemical processes, mineral carbonization is also one, but many of them, in particular chemical processes, need also hydrogen as a reactor. There are project initiatives in Europe. This is Carbon to Chem, Stellanol, Fresmi, and CO2Min. These are initiatives in Germany, in France, mainly with the focus on producing chemical fuels. Third pathway is the carbon direct avoidance. Carbon direct avoidance means you are producing steel with a new steel making processes without release of CO2. That is mean without with a very low release of CO2. you will never can produce steel without carbon, because carbon is one of the most important alloys. You have to alloy. That means it's soon you add carbon to the steel, you will lose some carbon by oxidation, and this will definitely emit as CO2. What are the options? The options are using hydrogen and electricity. Hydrogen, of course, has to be produced via renewable energies, preferable via electricity. There are also several initiatives. Hybrid in Sweden is the most advanced process in which has a demonstration plant have already started, and they are operating the demonstration plant, and they have already produced direct reduced iron. The basis is direct reduced iron with hydrogen. Siderwin is a technology using electricity. This is electrolysis of iron ore. SALCOS is a direct reduction technology, similar to the hybrid, but they have a concept for the transition from natural gas-based direct reduction plants stepwise to hydrogen. SUSTIL is a direct steel making technology, smelting reduction with hydrogen in plasma state, and HYFOR is also a direct reduction technology based on hydrogen, but in different to hybrid and SALCOS, they are using fine ore concentrates, and thus avoiding also the pelletizing step for iron ores. Yeah, future steel making with hydrogen. What are the utilization of hydrogen? We have to. What does it mean for the steel industry? What are the challenges? What has to be tackled and to have to be solved? First of all, we have to utilize hydrogen. We need the production. We have to produce hydrogen from CO2-free sources, and the sufficient supply of renewable energies for hydrogen production has to be ensured. Another one is the distribution. The challenge here is the low volumetric energy of hydrogen. It has to be compressed. The transport is also an issue which is, for me, not solved yet. There are different options discussed. It's via trailers on road, tankers, gas network, pipeline. Yes, this is natural gas network is now under discussion. And yes, as already mentioned in the presentations before, the storage is still an issue which has to be solved. If we speak about renewable energies, we need storages for hydrogen or some chemicals where we can produce out of these chemicals then hydrogen for the steel industry. These are the triangle of challenges we can define for the steel industry. What is the current situation about hydrogen use? Yes, it's already in use. There are also tests for injecting hydrogen in the blast furnace. ThyssenKrupp Steel, for instance, they are using it. Also, partial replacement of coal by hydrogen by injection. This is something which will be maybe implemented soon. Hydrogen injecting to natural gas-based direct reduction. This is there are concepts available. From my information, it's not done yet. Application which is done already since many years is producing hydrogen as a protective gas, especially for annealing processes of steel sheets. And then the hydrogen will be required for this carbon capture and utilization and converting the CO2 to fuels in chemicals. Yeah, if you look at what is the impact of hydrogen, we can see here the CO2 emission of different routes. The first route is the route from blast furnace and basic oxygen furnace, which is the benchmark is 100%. If you compare it with production of DRI based on natural gas and electric arc furnace, assuming also 400 grams CO2 per kilowatt hour for energy for producing electricity for the electric arc furnace, then we can get also already nearly 40% CO2 reduction. It's already a good benchmark. EAF scrap production, just charging scrap, is definitely a good option. It would mean we could achieve this 20%, this 80% reduction of the CO2 emission. However, the problem is the availability of scrap is not sufficient for producing the amount of steel in Europe which we need, and this is the one point is the amount. The second point is also the quality of the scrap does not meet the requirements to produce high steel qualities as you can do it with the POF or DRI EAF route. The option which gives you the possibility to produce steel with high quality based on iron ore as an input is the direct reduction route in combination with electric arc furnace and direct reduction with hydrogen. And which has from nowadays, from a point of technological readiness level, a high level. And we can expect that this technology will be implemented as the first one in the next. Another alternative, but the level is far lower, is the hydrogen plasma smelting reduction, where we achieve the same CO2 emission. The charming concept of this process, you can produce steel from iron ore in one step. We don't need these two steep steps like we have in DRI production and then melting the EI and EAF. This will be done in one process step. Yeah, these are already mentioned. What are the initiatives? One technology I did not mention was the splash iron making technology, which is also using hydrogen gas and in combination with methane, but it could be also methane from renewable energies. This is a development which is done in United States. Hydrogen plasma smelting reduction, hydrogen-based direct reduction, I already mentioned before. Yeah, this is a comparison of the conventional blast furnace route with the combination of direct reduction plants with melting unit. From the methodological point of view, is that by using hydrogen, you have the emission of water, process gas, using natural gas. You have also water emission, but some CO2 emission is still there. And this combination direct reduction plant with electric arc furnace is really seen as a bridge technology, starting first with natural gas as a fuel, and then switch over step by step to hydrogen, depending on that how the hydrogen business, hydrogen supply will develop in future. This is what can be done. It's hydrogen reduction. We can implement in parallel to an existing blast furnace POF installation a natural gas-based direct reduction, which then can be converted to a hydrogen-based reduction by increasing the hydrogen content in the reducing gas. Or this will be, I would say, a midterm scenario for the next 10 years, which we definitely will observe. And depending on the availability of this hydrogen plasma smelting reduction, which I expect by end of the third, and we maybe this technology become also as a further alternative to produce steel. Yeah, come now to my conclusion. Hydrogen in steel industry, we have opportunities, we have constraints. Maturity levels and integration is definitely a topic. We have many brownfield installation in Europe with blast furnace technology. You have to install there and integrate there a direct reduction plant in the first step with electric arc furnace. This is definitely a challenge. What is further is the availability of electricity, if you calculate to substitute the complete BOF route by the DRI hydrogen EAF route, this would result to an this would result to additional 500 terawatt hour of power. And this means a huge investment in the energy system. Also, the contribution of this power will be a challenge. Investment costs, definitely we need high investment costs, and this cost, who will pay this? Can we get funding from the European Union? On the other hand, we have opportunities. We see industrial symbiosis, other industries, chemical industry, or it could be also, for instance, cement industry. The reduction of the CO2 target, we see also that there is a demand on CO2 lean steel. Within the Europe, we already get the demand from specific steel users on steel with low CO2 footprint. And yes, favorable is, of course, is that we become independent from import of fossil fuels. And yeah, we see as well also the opportunities for the steel industry if we use hydrogen as a energy and reductant chemical. Okay, thank you very much for your attention. I'm happy to answer your questions in the discussion.
Thank you very much, Johannes, for this comprehensive run through where hydrogen fits in. We have a few questions online. Could you bring all the speakers the screen, please? And maybe if you stop sharing, Johannes.
Yes, I stopped.
Well, thank you all. This was very stimulating and interesting talks. And I know I have lots of questions, but maybe some of them are being answered online. So who's looked in, we actually can see the answers that put in there. But I want to sort of start perhaps by challenging Cedric a little bit, and of him saying, let's electrify everything as the way forward. And the question is this. We all been planning for 2030 or 2050, and that's a short term sort of in anybody's mind. And hence, I wonder if we have electricity available, would it be more economical or more beneficial for the environment to decarbonize domestic consumption or electrical consumption first before we turn our attention to processes that are currently being used sort of in industry? So is heavy industry a priority as compared to electricity in general, which is almost a third of our emission? We can't hear you, Cedric.
Yeah, can you hear me now? Good.
Yeah.
Thank you for the interesting question. Of course, it makes full sense in a cost priority order to start with decarbonizing the electricity we already use as electricity. Exactly like it makes full sense to start making green hydrogen for the hydrogen we already use, because we use it as hydrogen because there is no other way to refine fossil fuel or to make ammonia or to make methanol. Or to make ammonia for fertilizers or mining explosives, etc. So yes, indeed, it's always economically sound to start decarbonizing what already exists, where you already have a market for your electricity. But then I don't see a big a big reason not to go decarbonizing industry as you go decarbonizing transport or buildings with heat pumps and transport with batteries, etc. We need all of them. The perception is that it was more difficult to decarbonize industry, and my take is that for a long time people have only considered basically two areas of action, one being energy efficiency improvement, but in some cases, as Gus showed us with alumina, we're getting close to the theoretical limits. So there is no big gains anymore. There are gains in having the worst plants in the world, the oldest ones, being improved or replaced by more modern ones, but the more modern ones are close to the theoretical efficiency. So there is no big room for improvement anymore. And the other was carbon capture and storage, but we're not going to have that huge amount of carbon capture and storage that if you leave 15 gigatons or 20 gigatons of CO2 emissions, this appears to me unlikely, because it would mean developing an enormous machine for something that is finally always an added cost to what we do.
Yeah.
What I see with renewables now is that we have lower cost electricity, lower than we ever had. When you have, you know, and that's a revolution. That's a big change. When you have electricity getting close to 1 cent per kilowatt hour with PV and 2 cents with wind, and that's where we're going. It's another world, and we can do a number of things we never thought of doing.
Well, okay, you make an interesting point about the industries that we considered. Johannes showed us how much metal recycling is prevalent in his industry. Gus showed us that we almost to the theoretical limit. And Anne showed us that, you know, there's ways by which we cut today. We cut sort of CO2 from cement industry through, you know, blending and through other means. So there is way more than sort of electrification, I guess, with technologies that is available today. So my point is not that we should not electrify. My point is that if there's a pressing need to do it today, where the priorities will be. So the rate of adaptation is important. But let me ask you, Hannes, about hydrogen plasma in particular, and its potential, because the quality of the ores that we're digging is becoming less and less sort of desirable, and it appears that this technology it has a promise. What you haven't talked about is the dollar sign. So yes, these technologies are available. Are they using hydrogen or using, you know, for direct reduction, or hydrogen for plasma? But is it too expensive, especially in an industry which is very competitive and obviously capex heavy?
Yeah, we concerning the technology, we made already mass and energy balances for industrial processes, and there we can meet the same energy demand as we have with a direct reduction plant based on hydrogen with electric arc furnace. This is our benchmark. We are not comparing us with a blast furnace and BOF plant. Here we would be even better from the energy point of view, but this is a different story. This is the interesting thing is with this hydrogen as a reducing agent, you can do things which with carbon are not able. That you can, if you ionize hydrogen, it is a very, very strong reducing agent, which is very favorable for producing, you're reducing iron oxide. And the good thing, you can really directly go to steel, or say to crude steel. And this is the interesting point also from the perspective of investment costs, because you are saving investments. You have more or less the investment of electric arc furnace plus some auxiliary with, for maybe for the ore preheating system what you need. But this is a very, from the capex cost, a very interesting approach. However, the technological readiness level is far behind that what we have as a direct reduction plant with electric arc furnace.
Could you briefly comment also about using ammonia instead of hydrogen? Because as you
Yes.
mentioned correctly, storage and
This is-
transport is a problem.
This is, we have already discussed about that. Now we are doing it with hydrogen, the trials. In principle, would be also ammonia possible. The only thing is we have to recycle the hydrogen, and the hydrogen is not 100% converted to water in the process. You have a certain utilization degree. You have to separate the water. This is easy, but you have to then recycle back the hydrogen. As soon as you need ammonia, and to crack ammonia, you're forming hydrogen and nitrogen, then you have a high level of nitrogen, and this could be then the recycle rate. You need additional separation of hydrogen and nitrogen, which is a technical challenge. This is not
Okay.
easy to do.
Gus, Apple wants to have sort of carbon-free products, and obviously they use a lot of aluminum in their products. Is this technology available anytime soon? And the other thing, you comment about, you talked about using steam for calcination of the gibbsite. Could you comment about what other calcination can be used with steam?
Yeah, thank you, Bassam. I mean, I guess with aluminium, the typically somewhere between 70–75% of the CO2 comes from the second stage of the process, which is the alumina to aluminium. So this is why commercially already there are carbon 4.0 products on the market, because the alumina is, although it's a more challenging step, but it is more, it's a less significant component of the total CO2 of aluminium. So certainly low carbon aluminium is already commercially available from those plants which have access to low cost green electricity. The step to alumina is more challenging, but again, the some 2/3 of the CO2 emissions of the alumina step is in a low temperature steam side. So that is also closer to commercial reality, although it's still not commercially proven at the scale of alumina plants. But the production of low carbon steam is relatively close to market. And so we don't see any major problem in that being achievable by 2030. The high temperature step is then a relatively small component of the total emissions, but it is a little bit further away. We do think that it is plausible to get there economically, but it will require some evolutions of the process. Nevertheless, we're also hopeful that some of those can be done with relatively modest changes to a plant. So they may not require too much capex to demonstrate, but these are things that we have to complete a bit more investigation before we are ready to release them. But nevertheless, we think that that it's not that we can still make dramatic reductions in aluminium with technology that's largely commercially available, and then the final steps will take a bit longer. But I don't think we're too far from the kind of pathline that's needed, certainly for the 2050 time horizon. In terms of the calcination certainly calcination in steam is also being explored in some other processes, including in cement. And so there are also some potential opportunities there. And I know that a number of companies in Europe are also looking at this, and we're also looking at it, and we think there's some other potential opportunities there as well.
Okay, thank you. Any questions from the audience? Sorry, guys, I don't want to ignore you. Yeah, just wait for the microphone.
Just a quick question regarding the if we able to go to the green hydrogen or green ammonia, and then if we would like to compare the round trip efficiency of using green ammonia relative to the fossil fuels in gas turbine, for example, or in residential usage, do we have a number regarding this?
I think Well, it all depends what you have in mind. If you have in mind extracting hydrogen from ammonia, using ammonia just as a carrier because it can be transported on ships, it's already been transported on ships, while hydrogen is very, very expensive to transport on ships. That's what the Japanese research program on energy carriers has shown. Ammonia is really cheaper to transport. But if you want to extract it, as Johannes mentioned, it's difficult, it's costly. If you want a high purity hydrogen, it's really a problem. If you want a 5.9 purity, then it's really energy consuming, etc., and you end up with a very low return efficiency. If you want to use ammonia itself as a fuel, which can be done in internal combustion engine and can be done in turbines, then you can achieve to 35% round trip efficiency, which is of course much lower than what you have with batteries or even with pump storage hydropower, but which isn't bad if you consider that then you can keep your ammonia in a steel tank or your hydrogen, of course, with slightly higher return efficiency in a saline cavity for months without losing any of it and with little long duration storage cost. Then it makes sense when you want to improve the energy security, the electricity security of your system or your plant, and you want to have a safety week or 2 weeks of fuels to face what the Germans call the Dunkelflaute, the week without wind and without sun, or low winds and low sun. You want to face that once a year or twice a year. It's a week, it's 10 days, and that you can keep, then you don't care too much about the low efficiency. But you would not, I think you would not make heavy seasonal transfer with that because of this low efficiency. It becomes problematic. The true solution to the seasonal differences between the resources and the demand, the variation of the demand, is in having the right mix of solar and wind before all. In a sunny country, you will have much more solar because your electricity demand is in summer. In temperate countries, you will have much more wind because you have winds blowing in winter and at night when your demand is high.
Thank you. Maybe a quick question to Anne and then to Badr. I'm conscious of the time. So you're saying that we could reduce it by 50% or even more. Why didn't happen? Is what you're saying it's all about policies, or it's really about governments taking the right stands? Is there any other impediments why we haven't decarbonized cement?
When we talk about this new cement, where we only use 50% of the clinker, the fact is that the recipe of this new cement went out of the lab only 5 years ago, which means it's really recent. The cement industry is working a lot on this, and especially they are working, how could I say that, secretly, in order to put their hands on clay deposits. What happened is that previously they were very dependent from alternative cementitious material like fly ash and slag. And I can remind you the price of slag is equal to the price of clinker. So I think they changed the strategy and they really want now to put the hands of clay deposits in order not to be linked to a third party. But it's growing more and more. We have already one cement plant producing this new recipe in Ivory Coast. It was built by the Turkish government, OYAK group. And a lot of other cement plants will come on stream with this new formula in the coming 5 years. So it's coming. It's just because it went out of the lab 5 years ago. And the standards, the new standards, are just out here last month.
Great. So it's early time, but you have promised that it's going to happen, yeah? By the way, there's lots of questions online, and I want to encourage the panelists to look at them while we're talking. And I'm conscious of the time. I want to ask Mr. Badr a last question, if I can. And that is, you showed us lots of plans. Did Ma'aden implement any of those? And if so, sort of what's the capacity for the next few years in terms of renewable energy?
Yes, the main reason for that we didn't implement, especially for the renewable energy power plant, the regulation prohibits us from connecting to the grid as of today. They promised they will change this regulation for renewable energy, especially renewable energy power plant. And after that, it will be more feasible, more economical to generate more power to cover the mines 100%. And if we have surplus, we will send it, we will wheel it to other locations, which is connected to the grid. Now we will start with just PV panels, which we did for one mine now, and we will continue for all new mines. For the existing mine, the lifetime is short, so the feasibility will not be visible to make PV panels or wind turbine just for that mine, which will close within maximum 5 years. Mm-hmm. And this is the main reason. It's regulation plus the mine life.
Okay. All right. Well, so basically, because it's too far away and it has to have its own, it's not connected to the main grid, of course. Yeah. Okay. Well, thank you much for that. There was a question online about the slides. We will ask for the slides and we will share them with the registrants if they agree. So those will become available to all registrants. We won't have time to go through all the others, but before we finish, I'd like to ask the two panelists to come to the front, please, because we have a small gift for them. And those online, yours is on the post. It's a small gift that we have from KAUST to say thank you. Perhaps I'm going to pull one out. It's a little bit hard to, but let me see if I can. Sorry about that. All right. So this is what it looks like. I hope you'll be able to see it. I come in here. A simple thing from KAUST, basically, with your names engraved over it, say thank you for your contribution. I hope you'll be able to see it. So this is for Anne.
Thank you.
Oh, in fact, it's not for Anne. This one is for Anne. That's for you. Thank you very much. And you don't have to put it. Yeah, okay, it's all right. And that's for you. So thank you for your contribution.
Thank you so much.
All right, please join me in thanking all the speakers again. You're welcome to stay online if you like, because we're going to run a short video that basically it's a virtual tour. If you have been here, we would have taken you to our lab. This is not all our lab, but it's only a small part of them, but it will fit within the time frame. So could you play the video, please, again? And let me personally thank you all for your contribution. It was an excellent session. Thank you very much.
In the Advanced Laser Diagnostic Lab, we develop novel strategies to overcome existing limitations of combustion diagnostics. The corrugated picosecond Raman spectroscopy temporally separates the Raman signal from soot incandescence and laser-induced fluorescence, enabling interference-free Raman measurements in mildly sooting flames. The Hydro, our hyperspectral 2D Raman analyzer, allows 2D Raman measurements of temperature in major species in high-pressure, non-sooting methane air flames. It also allows for high-precision 1D Raman measurements at 10 kHz. We have extended interferometric Rayleigh scattering velocimetry from point-to-line measurements with our novel design based on a virtually imaged phased array. The diagnostics will be employed to study combustion in small channels and supersonic combustion. In the Combustion and Pyrolysis Chemistry Laboratory, the gasification and pyrolysis of different residues such as biomass and heavy residues from crude oil are investigated. Fractions from various feedstocks can be separated and investigated independently in our different reactor facilities under fixed temperature, pressure, and residence time conditions. In addition, we perform high-fidelity numerical simulations using quantum chemistry, kinetic rate calculations, and molecular dynamics to understand oxidation and pyrolysis in reactive environments. For gas phase systems, we conduct experiments in flames and jet-stirred reactors to understand chemical reaction mechanisms and determine associated thermokinetic parameters related to oxidation of different types of fuels. In addition, we have special reactors for studying catalysis under heterogeneous gas-solid environments. In this lab, we measure the electric field of plasma-assisted flames by a laser technique called EFISH, for electric field-induced second harmonic generation. A methane air flame is ignited in a stagnation flow burner. This flame can be seen here with and without plasma. To measure the electric field, an infrared laser is focused on the flame region, a part of which will be changed into a green beam. The beam's intensity is proportional to the laser irradiance and the electric field squared. This technique can measure the electric field during plasma actuation of the flame, which is crucial for the understanding of plasma chemistry. Welcome to Building 7, our high-hazard H5 classification lab space, where we house most of the larger-scale projects. KAUST was built to Saudi Aramco standards for petrochemical plants. The sophistication of the toxic gas management system is clearly evident on the walls in this corridor. The lab is capable of providing 0.5 kilograms per second of airflow at 45 bar continuously, plus an extensive fuel delivery capability including hydrogen, methane, ammonia, and various liquid fuels. The high bay area, with a ceiling of 12 meters, contains several large, high-pressure experiments. The centerpiece is the high-pressure combustion duct, the center's workhorse for studying canonical flames at pressures relevant to gas turbines and internal combustion engines. Here you see a high-pressure ammonia swirl flame and a part of the laser-based diagnostics being developed to measure a wide range of major and minor species. Also in this lab is the heterogeneous auto-ignition rig, designed to study the combination of chemical and physical delay in the auto-ignition of real fuels at pressure. This lab also contains the pressure gain combustion rig. This rig is used to investigate an alternative to constant pressure heat addition in gas turbines using constant volume heat addition. This isochoric heat addition results in an increase in stagnation pressure and hence thermodynamic efficiency. We are investigating acoustically resonant deflagration waves using either passive or active valving to demonstrate pressure gain combustion at elevated initial pressures. With the growing interest in hydrogen and ammonia, we are investigating the feasibility of converting a conventional natural gas-fired microgas turbine to an ammonia, hydrogen, or ammonia natural gas-fired gas turbine measuring both the performance and emissions from a commercial device. In this lab, we have two experiments, the new very high-pressure constant volume combustion spray rig and the turbulent flame speed rig. The spray rig is designed to handle pressures up to 300 bar to investigate next-generation isobaric combustion using a pre-burn to generate the necessary temperatures. This vessel will also be used to investigate supercritical carbon dioxide oxy-fuel combustion at pressures relevant to the alum cycle. Note both of these rigs take advantage of the blast-proof control room and can be operated from this room for safety. The second experiment allows for the investigation of chemistry turbulence interactions by measuring turbulent burning velocities at various initial pressures, temperatures, and turbulence intensities. The isotropic turbulence intensity can be controlled via 4 high-speed fans. Using Schlerin imaging, the expanding combustion wavefront can be measured. Here we see a laminar stoichiometric ammonia plus DMM in air flame at 5 bar. From these images, we can calculate unstretched laminar burning velocity as well as Markstein length. The turbulent flame shown is an ammonia flame in oxygen-enriched air at 3 bar. This is the Chemical Kinetics and Laser Sensors Laboratory. The 2 shock tubes are designed to study fuel autoignition chemistry and elementary reaction rates. We can assess pressures beyond 100 bar and wide range of temperatures. Various laser diagnostics ranging from ultraviolet to mid-infrared range are employed to follow the evolution of reactants, intermediates, radicals, and products. Simultaneous end-wall and sidewall high-speed imaging helps investigate inhomogeneous ignition. The laboratory also houses a twin-opposed piston rapid compression machine to investigate fuel autoignition at low temperatures. Laser diagnostics have been used to ascertain the validity of homogeneous core in the RCM. An optical combustion chamber is used to study the occurrence of pre-ignition and supernova. New laser diagnostics and sensors are designed for specific applications. Recently, a novel difference frequency generation laser system has been constructed to assess the bending vibrational modes of aromatics in the 12 to 15 micrometer wavelength range. Equipped with 7 engine test benches, the research in our internal combustion engine labs is focused on studying novel concepts and technologies to reduce the carbon footprint and pollutants emissions of the transportation sector. Here, our all-metal heavy-duty single-cylinder research engine is used to study the pre-chamber combustion concept as part of the FuelCom 3 project in partnership with Saudi Aramco. Different pre-chamber designs are being tested and evaluated to identify the key geometry features to reduce fuel consumption, NOx, CO, and unburned hydrocarbons emissions. Our testing setup is capable of measuring the engine indicated efficiency and emissions with high accuracy and high precision. The engine is operated in well-controlled conditions, which ensures the reproducibility and repeatability of our experiments. In this project, our ultimate goal is to improve the efficiency of spark ignition engines while reducing emissions to near zero levels. Our labs are also equipped with 4 optical engine test benches. They are designed to allow full optical access into the combustion chamber through an optical piston and liner made of high-purity quartz. Here, our optical heavy-duty single-cylinder research engine is used to study combustion in an optical pre-chamber. High-speed chemiluminescence and a variety of laser diagnostics reveal the physics behind the observed trends and provide detailed data sets for calibration and validation of numerical model. Our ultimate goal is to perform advanced laser diagnostics to study the pre-chamber combustion. This relies on developing new optical techniques and adapting their operation to the engine environment. Using a near-term Grand Challenge grant from KAUST, the center was able to partner with Sustainable Energy Solutions in Utah to bring their cryogenic carbon capture process to the kingdom. Here you see the 3 shipping containers housing the components for this 1 ton per day CO2 capture scale rig. The rig is capturing flue gas from the corrosion rig and removing both water and CO2 with greater than 90% CO2 capture efficiency. Working with SES, we were able to de-risk several components, giving us confidence to move up in scale to a 25 to 30 ton per day facility. Due to the cryogenic process, we are able to simultaneously remove sulfur dioxide and nitrogen dioxide as well as CO2. We are developing novel direct contact cryogenic heat exchangers to improve the thermal effectiveness and hence increasing the overall efficiency.
Hello, everyone, and thank you for joining this session 3.2 with the title Renewable Technology. I'm Aldo Steinfeld, and I'll be chairing this session, and we have a list of excellent speakers this afternoon. And without losing any further time, let me introduce to you the first speaker, who is this is a keynote presentation. So I'm glad to present the keynote speaker, with Professor Al Weimer from the Department of Chemical and Biological Engineering at the University of Colorado. Professor Weimer is an international renowned scholar in the field of chemical engineering. He has made seminal contributions in the fields of hydrogen production, solar reactor design, particle fluidization, atomic layer deposition, and advanced ceramics. He has supervised 29 doctoral theses, is the author of over 200 reference journal papers, 48 patents, so an outstanding publication record. And he's the recipient of many honors and awards, and I would like to mention just 3 of them. The AICHE Research Excellence in Sustainable Engineering Award in 2015, the AICHE Lifetime Achievement Award in Particle Technology in 2017, and also I want to mention an award from his time in industry. He received the Dow Chemical Company Excellence in Science Award. A pleasure and an honor to introduce your talk, Al, entitled 2-Step Solar Thermal Water Splitting, the Path Forward. We are very much looking forward to hearing your talk. So I guess you can share the screen now.
Yes, they won't. They have to turn the screen on. The host has stopped the video.
Okay, there you are.
You see me? Because I can't see it here.
We see a slide with your name.
Ah, there it is. Okay.
Now we can see.
Very good. Yeah.
Very good. And we see the Rocky Mountains behind you. Very good.
So Aldo, thank you for that introduction. I'll have to make sure that I talk about some of your work here. I also see that Hisham Idris is in the audience, and he's one of the co-authors on also some of our work. So it's nice to see Hisham there. So let me go ahead and get started. Yes, so We're going to talk about two-step thermochemical water splitting, the path forward. I appreciate the invite to present a keynote at this conference. And let me say that I have been to KAUST before. And in fact, maybe some of you in this photograph, you can see yourselves and you can tell me later on the chat or something. That'd be great. And I even rode a camel. So that was quite an experience, being in Riyadh and riding a camel at the University of Colorado Kingdom of Saudi Arabia alumni event. Okay, so let me just get started here. Let me just say that the sun is a 5,800 Kelvin black body. If you're looking at those temperatures, natural gas and oxygen maximum temperature about 30, 43 Kelvin. Nuclear fuels maybe 1300 K max. And if we convert this to electricity in order to achieve higher temperatures, we typically take an efficiency hit of maybe 30 to 50%. So as you can see here in the photograph, right, we're looking at a magnifying glass. So if you ever used a magnifying glass and fried the ants, you certainly have solar thermal genes. But this process is actually sort of expensive, right? Nobody would ever do this. And I like this quote from Professor Fletcher, who passed away a couple of years ago. Basically, that because of this 5,800 Kelvin black body radiator in the sky, it really behooves us to invent, develop processes that take advantage of this thermodynamic heat source. So in order to cost effectively achieve these kinds of temperatures, we use heliostat fields. Here we're looking at the Crescent Dunes heliostat process for essentially molten salt, steam, maybe getting up to about 500 Celsius. The concentration of sunlight here is less than 1,000 suns. And in order to achieve higher temperatures, and here we're looking at the efficiency of absorption, idealized efficiency as a function of cavity temperature. And what you can see is that we have to basically overcome temperature to the fourth, impacting negatively the efficiency. And we can do that by increasing the concentration of sunlight. So if we look at temperatures that we would like to achieve, concentrations of sunlight, the operating sweet spot, if you're using a containment material, is somewhere between about 1,200 and 1,500 degrees Celsius, because at this point, radiation kicks in for rapid heat transfer. And we also have silicon carbide available that can be used in oxygen-containing atmospheres up to about 1,650 degrees Celsius continuously. And you'll also notice that in order to achieve efficiencies of approaching 80%, we're looking typically at concentrations on the order of 1,000 to 5,000 suns. So the idea is, how do we get there cost effectively? And we basically use heliostats and for higher concentrations, secondary concentrators. We're going to be talking about water splitting. I show some different types of processes for being able to achieve renewable hydrogen from sunlight. You can see here photovoltaics combined with electrolysis, or CSP with electrolysis. We're looking at efficiency of somewhere around 13 to 14% to get the hydrogen. Whereas with concentrated sunlight, we don't take the efficiency hit in converting the energy to electricity. And so we can directly take the sunlight, concentrated sunlight, and drive chemical reactions. We avoid that efficiency loss, and we can achieve theoretical efficiencies that are about 2x that of a PV or CSP combined with electrolysis. So that's the reason that people are looking at what I'm going to call concentrated solar power for solar thermochemical fuels. And of course, here's an idealized system where we would basically use concentrated sunlight to split water take that hydrogen, drive a fuel cell. The oxygen is then recycled back, get water back out of this, and we repeat that process and have that sort of in situ fuel cell type of process. We can also look at vehicles, mobile systems. Here I'm looking at the Toyota Mirai. I don't know if they hit this sales volume yet, probably not, right? But I've always found it interesting that the fuel cell vehicles were ahead of the electric battery vehicles for a number of years. And then in the last maybe 10 years, the battery vehicles have really come on strong. But now I know there's a substantial interest in hydrogen sales as well. And the state of California has huge incentives for using renewable hydrogen. So the process that we're looking at is a reduction oxidation process, and I'll talk about this here in a little bit more. Basically, the overall reaction is going to be water plus solar energy to produce hydrogen and oxygen in 2 steps. You could then use a fuel cell and get the water back and electricity. And basically on these 2 steps, we use a high temperature reduction with concentrated sunlight, typically in the range of maybe 1400 to 1550 degrees Celsius, could be lower, 1350 C as a target. And then we follow that up with that reduced oxide, and we then oxidize that with steam at a higher temperature, typically 800 to maybe 1350, 1400 degrees Celsius. And the key to this is really what I'm going to call the magic foo-foo dust. So the active material here, and really we have a fluoride structure, perovskites, and spinels are the 3 types of materials that have been investigated for being able to carry out these redox reactions where these materials are robust. Basically, they are not going to sinter and deactivate like some of the ferrites and some of the original materials in the past. And there's a huge amount of work ongoing looking at developing new materials using density functional theory and other computational work in order to identify what those materials might be, those promising materials, making those and then testing them. And as I mentioned here, the displacement mechanisms, basically some of these involve phase changes, and typically the experience is that when you have a phase change, you end up with sintered materials that then deactivate over time. However, these fluoride structures, ceria, perovskites, and spinels appear to operate through some kind of an oxygen vacancy mechanism. They have a stable matrix, and those materials are robust, and those cycles can be repeated theoretically and indefinitely. So these are the materials that are targeted for development. And if we compare these, cerium oxide, ceria is the state-of-the-art material, and I'll talk about that here in a second, why that's the case. The major focus of research groups is perovskites, and then we are sort of the lone ranger out here looking at spinels, in particular iron aluminate in terms of the active material, and we'll talk about that here as well. You have 2 types of solar reactors. We can broadly separate those into directly irradiated and indirectly irradiated. So directly irradiated solar reactors would have some kind of a window. The sunlight directly heats the active redox material, which has typically been a powder. For indirectly irradiated materials, you would have to go through a solid containment. And so the heat transfer, the efficiency to heat the solids is much higher if you don't have to go through some kind of a solid containment. But there are also challenges with both of these that we'll talk about here in a little bit. So some examples of the directly irradiated reactors, of course, probably the first one, I'm sure, that received significant attention was developed in the Steinfeld group at ETH with the vortex flow reactor. There's a quartz window here. Sunlight comes in and directly heats the solids. Work was done by Kodama and co-workers in Japan, again, vertically mounted by a fluidized bed reactor with sunlight directly through a quartz window. And more recently, this is a schematic of a reactor that was used by Sandia National Laboratory and DLR and Bucknell University kind of combined. But basically, there happens to be a window where they heat the solid reactants up to about 1500 degrees Celsius and then carry out the oxidation at a much lower temperature, 800 degrees Celsius. So typically for most of the materials that are studied, people have investigated what's called temperature swing redox reactions. So high temperatures for reduction, lower temperature for oxidation, because thermodynamically that is favored. But in general, the windows are a problem with powders due to thermophoretic deposition. So thermophoresis, what happens is you have fine powders and they are going to have a thermodynamic driving force to move them towards the colder surface. So if the sunlight is coming through the window is colder than the solids. So the solids are going to want to move towards that window. If you have particles on top of that window, you could end up with vitrification of the quartz and essentially breakdown and destruction of that window. However, that has been overcome by using foams or reticulated porous ceramic materials, where now we have a fixed bed. So now the solids are fixed. Here we show a paper originally published in Science, and I'll talk about that here in a little bit. This was a collaboration, ETH Zurich with the California Institute of Technology, Cecina Hales Group with Aldo Steinfeld. And here you can see Syria was reduced at 1500 C, oxidized at 900 C, a number of papers that are related to this. And I believe this is still the highest efficiency believable that has been demonstrated, about 5.25%. And what was really significant about this paper, and the reason it was published in Science wasn't necessarily that was the most efficient reactor or the best materials, but what these authors demonstrated was it was possible to actually carry this process out over many, many cycles, 500 cycles, carrying out reduction and oxidation, and to be able to produce carbon monoxide or hydrogen in that particular system and have very robust active materials. Very, very significant. And this is the reason why Syria is considered the benchmark material. Now, we've done work with hersenite, iron aluminate, and the point I want to make here, this is also temperature swing, reduction at 1500 C, oxidation at 1350 degrees Celsius, looking at about 300 micromoles per gram per cycle. You can see that after about maybe 30 cycles, that stability of the matrix, basically we don't lose any activity for the remaining 200 cycles in that particular system. So hersenite is also robust, and these experiments were carried out in a stagnation flow reactor heated with electricity. We've also done work with density functional theory. We've done some in situ high temperature XRD. And here, what we show again is that the matrix is stable. We can carry out those cycles, and essentially the hersenite is a stable material undergoing an oxygen vacancy type of mechanism. And we can see that here we're looking at cobalt doped hersenite versus the zero cobalt hersenite. You can see that the kinetics are faster for cobalt doped. There's higher productivity for the hersenite, and also differences in temperature. As we increase the temperature, we end up with faster kinetics in the production of hydrogen. More recent study published last year in Chemical Engineering Journal, which you can see here. Again, this is for 50% steam on the oxidation reduction at 1450 C, producing carbon monoxide from CO2. And first of all, the fuel production decreases with an increase in the cobalt content. And we believe that defect energy increases when cobalt's added to the iron aluminate, resulting in lower hydrogen production. But you will also note that the rate of reaction is much faster with an increase in the cobalt content. In fact, up to a 4 times increase in rate with a 40% cobalt additive. And again, cobalt is increasing. We believe the number of active sites, the vacancies at the surface, in order to speed up those reaction rates. Now, we have also demonstrated that we can carry out isothermal operation. So without change, without doing temperature swing, but with uniform temperature, we can, in this particular case, use hersenite to show that it's possible to produce hydrogen at a single temperature with reduction and oxidation occurring at 1350 degrees Celsius. We've also demonstrated that based on chemical potential, we can increase the production rate by increasing the concentration of the oxidant. So again, here we're impacting the steam partial pressure at 1350 C for isothermal water splitting and showing that we have the ability to increase that rate. So we looked at demonstrating this, scaling this up. We were part of a grant from the Department of Energy, and the final deliverable of this grant was to be able to produce 3 liters of hydrogen in an 8-hour period on sun. And so we ended up fabricating large quantities of hersenite materials. We used a dynamic mixer. Here's an IRIC intensive lab mixer to make these particles that were hundreds of microns in size, basically using just aluminum oxide and iron oxide particles less than 10 and 5 microns. So this is not an expensive precursor, using starch and melted dextrin as a binder with water, dried at 150 Celsius for 4 hours, pyrolyzed, calcined at 1300 C under vacuum. And here you can see the formation basically of hersenite. We then took these particles and we used a multi-tubular reactor at the NREL high flux solar furnace on sun. NREL has a large heliostat that captures the sunlight, directs it to a secondary concentrator, primary concentrator. It then concentrates the sunlight, sends it into a building, and our reactor sits in the corner of this building. And with the availability of a secondary concentrator, we can achieve sunlight up in the order of 2,500 suns. So in this system, we happen to use 2 1-inch tubes, silicon carbide for fluidized beds, 40 grams of hersenite at each one. This is what it looked like on the mesa in Golden. And this was our solar reactor. And here you can see basically a 10-centimeter diameter solar comes into this mirror and then wraps around the tubes that are within this mirror. So theoretically, we have multi-tubes inside this system with a CPC using sunlight. And again, this is indirect irradiation. So we ran these tests with 2 different types of operating modes. One was we had intermittent on-sun testing, where we had those 2 tubes, both of them were being oxidized and both of them were being reduced. Here you can see the production rate of hydrogen, and we were able to produce 5.3 liters in 8 hours. So we achieved the 3 liter in 8-hour goal, and producing somewhere around 600 micromoles per gram of hydrogen. Now, what I don't show you, right, this is real sun, clouds are coming by, you're dealing with all kinds of different issues, difficult, to control temperature, but this was on the order of 1300 C isothermal processing. We also looked at a continuous process where we had 1 tube reducing and 1 tube oxidizing, and then we switched them. The tube was oxidizing, was now reducing. The tube was reducing is now oxidizing. Again, very difficult using on-sun heating with the solar furnace. And we were able to produce about 550 micromoles per gram, 1 liter of hydrogen in a 2-hour period. So we were really ecstatic about this, being able to achieve the final deliverable for the Department of Energy, and really the first demonstration of continuous isothermal cycling on sun. We evaluated the particles after that testing. We didn't see any sintering of the individual particles. After 3 days of on-sun cycling, the spinel phase was maintained over those 3 particular days, and the hersenite composition was constant over the on-sun redox cycling. Now, as a comparison, I think it's interesting to compare the results of hersenite with the indirect heating with what I consider probably the most extensive direct heating on sun also with real sun. This is cerium oxide in a foam form using a 45 kilowatt thermal furnace. NREL's 10 kilowatt. We talked about the performance of the hercinite at 1300 C isothermal. In this particular case, the cerium was reduced to 1550 C reduction temperature, and the oxidation occurred at 1100 C. And you can see they were able to produce about 4 liters of hydrogen in 8.5 hours. Pretty comparable. And again, the production rate of ceria per mass is typically maybe one fifth to one. It takes about 5 or 6 times as many cycles in ceria reduction oxidation to achieve the same kind of production using hercinite. But again, I find this to be a very interesting comparison between those two. Recently, there's been a paper published by the Cecina Hale group at Northwestern. This paper was just published in Matter in 2021. This is a calcium titanium manganese material, perovskite, outstanding properties and performance. And I think what's interesting to note here is that here we're looking at temperature swing 1350 to 1150 degrees C. The cycle time is about 1.5 hours, and it produces about 400 micromoles of hydrogen per gram. So these performance characteristics are very similar to hercinite. It's slower kinetically, and it has a higher productivity than the typical perovskites like SLMA that have been investigated in the past. So in terms of a path forward, and again, this is my interpretation, my thinking, and you may have other ideas, but I think that it's important to recognize that the competition for renewable hydrogen is probably PV-driven electrolysis. That efficiency is about 14%, but that can be done today. Okay, it might be expensive. Electrolyzers are expensive. Efficiency maybe 65 to 70%. But I think, you know, PV has kind of won that game when the sun's out relative to CSP because of all of the experience basically building PV arrays. You can put them on virtually any building in the world where there's sun without having to worry about getting a permit. And solar thermal, if you look at these giant towers in the Mojave Desert, the reason they're in the Mojave Desert, right, is because of the permitting that would be required if you try to put those somewhere else. And so there's not a lot of practice in building CSP systems. And so I think the cost can be driven down if people start to develop smaller systems with shorter towers. You may pay a penalty with regard to that in terms of size, but I think that would give an opportunity to be able to provide more opportunity. I also think that we need to look at running the oxidation reaction at pressure. If we want to supply hydrogen to a pipeline, or if we want to make syngas, right, there's a huge advantage with CSP versus the electrolysis, because we can split CO2 and water at the same time to produce syngas. And if you can do that at 30 bar, you can supply a process to make methanol to gasoline, or go to FT to produce diesel. There's also a need to maximize heat recuperation. A key here is how can we recycle the inert gases using the reduction step. And I think that the oxygen transport membrane has some cost issues. In talking to some of the producers of nitrogen, they came back and said that they could find a use for nitrogen that had some oxygen contamination if you're locating pretty close to a chemical plant. So that could also be an option, is to find uses for nitrogen with a small amount of contamination. I think we need to eliminate cloud-driven intermittencies. And in fact, try to eliminate intermittencies altogether. So if I look at this, and again, what we're doing at CU is we are focused on indirect irradiation using hercinite active materials. We have a hybrid solar thermal electric reaction process, a furnace Here you can see when you have sunlight, you can heat a reaction tube or series of tubes with sunlight. When a cloud comes by or in the evening, you can put a radiation shield in front of that cavity and you can heat with electrical heating elements. So you have the option of running 24/7 with sunlight and electricity. Here's a photograph of that system. It's a 18 2.5 kilowatt electric xenon lamps. And this is that particular receiver. Here you can see the CPC goes in here, and we have the sliding mechanism for a radiation shield. So with that, I want to thank you for listening. And I'd like to maybe answer any questions unless you wait till the end. Thank you.
Thank you very much, Al, for this very interesting presentation and for sharing these latest results you have obtained in the lab. I believe the question and answer will be done at the end of the session. Is that correct? We have the panel discussion coming up later on. So,
yes, that's true.
Okay, very good.
Okay.
So thank Alan, and stay online. Don't go anywhere because there will be questions to you later on.
Great, thank you.
So I'm happy now to introduce the second speaker of this session, Dr. Mehdi Jafarian. Mehdi is a senior research associate and lecturer at the School of Mechanical Engineering at the University of Adelaide. He received his PhD from the University of Adelaide in 2014, and his doctoral thesis was awarded with the Dean's Commendation for Doctoral Thesis Excellence. He also received an award for innovation in solar thermal energy storage from the Center for Energy Technology. His area of research is in concentrated solar thermal energy, and in particular with applications in chemical looping combustion, carbon capture and storage, and mineral processing. And this last application brings me to the title of his talk, Integration of Solar Hybrid Sulfur Cycle with Copper Production. Please, Mehdi, we are looking forward to your talk. Go ahead and share your screen.
Okay, hello everyone. Thanks, Professor Starfield, for the introduction and introducing me. In this presentation, I will talk about the integration of hybrid sulfur cycle with copper processing. In Australia, around 28% of the emissions is coming from mining and high temperature processes, while most of these processes at high temperature systems are in remote areas of Australia where it's difficult to take fuel. It's very costly to have fuels there, and there is vast resources of solar thermal energy. However, the integration of renewable hydrogen or renewable resources into these high temperature processes of mining has not been done yet. Hybrid sulfur cycle is a high temperature cycle for hydrogen and oxygen production, but the integration or use of hybrid sulfur cycle in copper processing has not been investigated yet. So the overall objective for this project was to assess the integration of hybrid sulfur cycle or HICE cycle with copper processing. Hybrid sulfur cycle actually is a chemical looping process in which sulfuric acid is the circulating component within two reactors. The system has one reactor where sulfuric acid at high temperature, around 600 to 1200 degrees C, cracks to sulfur oxide, oxygen, and hydrogen. And then after separation of oxygen within a gas separation unit, the sulfuric acid with some excess water is electrolyzed to produce hydrogen and yet again the sulfuric acid, which is recycled back into the high temperature reactor. So as I said, this is a kind of chemical looping process. Sulfuric acid cycles in the system. In first reactor, it produces oxygen, and in the second reactor, it produces hydrogen. But the good point about this process is that the electricity needed in this system is something around 1/7 of the electricity that is required through conventional pyrolysis systems. That means the rest of the electricity needed is supplied from concentrated solar energy, and we can have the benefits of low-cost storage or high-temperature storage for this system. Copper processing, on the other hand, as shown typically or schematically in this system, comprises 5 main stages. In the first stage, ore is crushed within a crushing plant. Then through a concentration unit, the fraction of ore that has more sulfide is separated. And then the high content of sulfide goes to pyro pathway. In the pyro pathway, using oxygen and fuel, the sulfide ores convert to pure copper. And then the oxidation of sulfide also produces SO2, rich gas, which is then converted to sulfuric acid within an acid plant. Inside the acid plant or within the acid plant, we need some fuel to preheat different streams, though the reaction of SO2 and oxygen is exothermic, but we need to burn some more fuel to get the reactions done, and we need some oxygen. The produced sulfuric acid then is used in another pathway, which is called hydropathway. In the hydropathway, the copper oxides are treated to produce copper and the waste. So the system requires hydrocarbon fuels or fuel and oxygen, which are produced both by the high cycle. So we thought there might be some economic potential for the integration of these systems together. On this basis, we've developed this process configuration to integrate high cycle with the copper processing. The system shown here comprises 2 main sections. The first section shown on top is high cycle with 2 reactors, as explained, and the solar thermal energy is used to provide the high temperature heat. So for the assessment, we've considered the particle reactors, the particle receivers, and where the particles are heated by concentrated solar thermal energy and stored. And then the stored heat is used to crack sulfuric acid, and the cold particle are stored for the next round of being hit with solar energy and storage. And the produced hydrogen is introduced into the copper processing, both into pyro pathway section and into the sulfuric acid. At the same time, the oxygen produced in the system is also used to provide the oxygen required in the pyro pathway or smelting reactors and the sulfuric acid pathway. So as you can see here, the high cycle can be designed either to produce enough hydrogen to run this system or to produce enough oxygen to supply the oxygen demand in the system. So actually for the assessments, we consider 2 scenarios. In the first scenario, we consider that the high cycle is sized to supply the hydrocarbon fuel required in the system. And in the second scenario, we consider that the high cycle is sized to produce the oxygen demand for the process. The main assumptions used for the assessments are listed here. I'll go quickly through some of them. We assume that we have a capacity of 5,000 tons per hour of the ore with 2% of the copper. And we also assume that the sulfide and the copper oxide ratio for the assessment varies from 10 to 90%. Also, the cost of hydrogen production from HICE, we consider that is 5 plus minus $1.2 Australian dollars per kilogram of hydrogen based on the previous assessments. Also, an extra cost for hydrogen, if we can sell it for $4, $10 per kilogram of hydrogen was assumed, and a copper production cost of around 4,500 Australian dollars per ton. Based on this assessment, based on these assumptions, this figure shows the cost of fuel and oxygen via pyro pathway divided by the copper product versus the sulfide content in the ore. I should have mentioned that as the fraction of sulfide in the ore increases, the fraction that goes into pyro pathway also increases. This figure also shows two lines, dashed lines here. The top one is the typical cost of fuel and oxygen in underground mines, and the green line, which is a bit lower, is typical cost for fuel and oxygen in open pit mines. The cost for open pit mines is typically around $200 Australian dollars per copper product, and the cost for underground mines is around $300. So our assessment shows that for two scenarios, if the sulfide content in the ore increases, then the system becomes more economic. And for the case, say for example, for scenario 2, if we can sell some of the hydrogen, the price becomes around $100 for the pyro pathway. But altogether, if the sulfide ore in the ore is higher, the economic value is higher. And the reason behind this, as I mentioned, is that when sulfide is more in the copper, then the pyro pathway becomes more important, and then more hydrogen is required there. And the second point is that if we size high cycle based on hydrogen production, then it's hard to become economic. But if we size it based on oxygen production, there is potential for the cycle to be economic. And that is because the amount of oxygen required in copper processing is way too more than the fuel required in the system. Through assessment also, we found that around 10% of the cost for high cycle comes from the reactors used for the dissociation or cracking of sulfuric acid. So we found a couple of catalysts, which are molten catalysts, and based on that, we are also developing a new technology for cracking of sulfuric acid to use a molten catalyst in this system. This figure shows a schematic representation of a solar receiver, which is called solar bubble receiver. The system comprises a cavity where concentrated solar radiation is introduced and absorbed, and this cavity is submerged in a molten bath, which is a catalyst. And then the gas, which can be sulfuric acid, for example, is introduced as bubbles or is dispersed into the catalyst and dissociated as it moves up, and the product gas goes out. This is a kind of typical configuration, and this can be this is for indirect heating, but it can be also configured in an indirect configuration and to be heated with different heat transfer mediums like particles or other high temperature heat transfer mediums. So we have also developed this receiver and tested under a non-reacting environment to start the assessment and find out and learn about the heat transfer mechanism in the system and the pressure drop, because most of the molten metals which are used in the system can lead to a high pressure drop in the system. So this figure shows the variations of heat transfer coefficient or local heat transfer coefficients around the cavity, around the azimuthal angle, for the cavity which is submerged in a two-phase gas bubbling flow regime where argon is injected in the system. And the variations are plotted for different Reynolds number at the nozzle, at the injection nozzle. And you can see in all assessed case, a high rate of heat transfer of more than 3,000 watts per square meter degree C, was achieved. And as the Reynolds number goes up, this heat transfer also increases significantly. But there is also variations around, along the azimuthal angle. This figure is another example of our results, where we have measured the average heat transfer coefficient over the cavity within the molten bath versus the pressure drop. And also you can see that as the pressure drop goes up, also the heat transfer goes up, which is a known trade-off between the heat transfer and the pressure drop. So opportunities that we think we can obtain from using a solar bubble receiver in a high cycle is that the high rate of heat transfer, because the molten catalysts that we have identified are also based on the liquid metals. And we think that we can achieve a very high rate of heat transfer around the cavity in these reactors. Also, we avoid sintering or other problems at the activation of the solid catalysts, because in liquid metal, there is no problem with sintering anyway. But on the other hand, it is difficult sometimes to have containment because of the corrosiveness of this catalyst and metals or molten metals. Also, there is limited data around this material, which makes it difficult, the assessments. But it also provides opportunities for temperatures of lower than 1000. If we can decrease the temperature, then we can mitigate the challenges with the containment of this material. So in summary, we found that the integration of copper refining plant and HICE for in situ hydrogen and oxygen production offers economic value, and the integration becomes economically favorable is if more than 70% of the copper ore is processed via the pyrometallurgical pathway, or the sulfide content of the ore is more than 70%. And we also found that the economic aspects of the process would be higher if we size the high cycle based on the oxygen production rather than hydrogen. And the use of bubbling flow, we think that can offer further potential to mitigate the costs. Finally, I would like to acknowledge the support of the Australian Solar Thermal Research Institute, or ASTRI, to support and to fund this project. Thank you very much.
Thank you. Thank you very much, Mehdi, for this interesting presentation, especially the design of your solar bubble reactor, quite innovative, and I'm sure there will be questions about it. So please stay tuned for the questions to the panel discussion.
Sure, thank you very much.
We move now with the third speaker of this afternoon, and I'm glad to introduce to you Professor Uwe Riedel from the Faculty of Aerospace Engineering at the University of Stuttgart. Professor Riedel is also the acting director of the Institute of Low Carbon Industrial Processes at the DLR, the German Aerospace Center. He has over 30 years of experience in modeling and simulation, reactor kinetics, reactive flows, combustion, and CFD. In particular, his research deals with the physicochemical properties of conventional and synthetic fuels, with a focus on aviation fuels. Professor Riedel holds a PhD in physics from the University of Heidelberg. And today he will be making a presentation entitled Role of Electrification in Decarbonizing Industrial Processes. Please, Professor Riedel, go ahead and share your screen.
Yeah, so thanks, Bassam, and thanks to Bill and all the organizers for inviting me. And I have been to KAUST before at the Future Fuels workshop in 2016. I had given a talk on alternative jet fuels, and that already had a connection to decarbonization of the transport sector. Since then, I've changed subject quite a bit, and since early in 2019. I'm the director of a new DLR Institute on low carbon industrial processes, located at 2 cities, about 1 hour and 3 hours south of Berlin. And as the name says, we are looking at CO2 reduction in industry. In my talk today, I want to cover the challenges for the industrial sector in reducing its CO2 emissions, talk briefly about the research we have started at the new institute, and of course I will give you my view on the options we have for the electrification of heat. What do we need to know about the industrial sector when it comes to decarbonization? About 30% of the CO2 emissions of the industrial sector result from the heat demand, today mostly covered by fossil fuels, and specific for this sector are the so-called process-related emissions, because some processes require carbon for its carbon content and not for its energy content. We have a strong interconnection of value chains in the sense that the output of one industry is input to the other industry, and this creates a delicate connection between industries, but there's no time to go into details on this today. We have a long lifetime of all the assets, wherefore it's highly critical to make the right decisions at the right point in time. And last but not least, specific for the industrial sector is the competition on cost in a global market. If we look a little bit closer into the type of emissions, we see here that about 2/3 of the CO2 emissions are related to the use of energy. So here, once the electrical power is sufficiently green, then electrification of heat can play a role. For the other third, other options are needed because the carbon is used due to its carbon content, and it's not only about the energy content here. So 2/3 of the emissions of the industrial sector, in 2/3 of the sector, there is the option for the electrification of heat. Now, this is one of the main research topics we have at the new institute. I'll be talking about our idea on high temperature heat pumps in a minute. And the 2 other departments work on the digital twin of industrial processes. We see this as a means to bring efficiency up and also as a means to minimize the risk in the transition to the new energy system. And then the third topic, and there's another department working on this, is the avoidance of process related emissions. Now, when we talk about heat, let's get the scale right. What is high? What is low? I tend to address the temperature range below 100 degrees C as the low temperature range. In this range, heat pumps are available, and there needs to be an increased use of existing technology to decarbonize industries having a demand in the heat range below 100 or 150. Now, more important to us at the new institute is what we call the high temperature range and what we call high temperature heat pumps. We have started the development to build up heat pumps which will cover the range 150 to 500, 600 degrees C. Beyond that temperature, we believe they can no longer be efficient. And let's say beyond 500, 600 degrees C, I address this temperature range as very high. We have again 2 options: the direct electrifications. We use the electrons, electrical power for resistive heating, electric arc furnaces, and the like. obviously indirect way using molecules, e-fuels, and hydrogen. In industry, it will be mostly hydrogen. So this is our picture, and to give you a more quantitative view on that, there is about a 50% demand in end energy in heat creation, and about half of the heat is in the range 500. And if we look at the light blue sector, we can look a little bit closer and see that 15% is not accessible for today's heat pump, but these 15%, this is the target of our new development we have started. We began to develop a pilot plant for now with a working fluid air, and we want to create what's called the Cobra, because it's based on a gas turbine Brayton cycle. We want to reach with the first pilot plant the range 250 to 380 degrees C, and combining heating and cooling together, we want to have a power altogether of around 250 kilowatts. So this is all new, and it's the beginning, and the next step is a bigger demonstration plant with power up to 10 megawatts, and we want to reach heat up to 20 megawatts in the range 300 to 500 degrees C, also using heat recovery at various levels. And also there are already plans to work on steam compression and the Rankine cycle to get a higher coefficient of performance and to get up to even higher temperatures. Now, what are the research questions connected to this? We need to optimize the cycle design for upgrading waste heat and ambient heat. We need to understand the dynamic operations, startup and shutdown operations. There needs to be work on heat exchangers to get more efficient and more compact heat exchangers. And we have to reduce the energy losses in the various components. So that's all ongoing work. I said it in the beginning, the institute is still young, and I'll keep you posted on our scientific results. And here at a summary, I termed that the priorities in the electrification of heat. I think first priority needs to be to increase the efficiency in each temperature range. And whenever possible, we should make use of heat pumps. And I termed that a leveraged use of electricity, because the coefficient, as long as the coefficient of performance is high enough, that's good use and efficient use of electricity. And for a really high temperature region, we have to be clear on the fact that this is hard to reach with high temperature heat pumps, but there are the options available using electricity directly, or in industry use hydrogen and maybe synthetic fuels for the decarbonization. And the new institute, and at the new institute, we set out to address all three priorities. And I said that already, keep you posted on first results. And this ends my talk, and I'm looking forward to the panel discussion in a while. Thank you.
Thank you, Professor Uwe, for your interesting presentation and showing you the different paths to perform this electrification. Please stay tuned for the panel discussion later on.
Yep.
We move now to the next speaker, and this is Professor Bassam Dali, and I'm very happy and an honor to introduce Professor Bassam Dali from the Mechanical Engineering Department Combustion Research Center at KAUST. There is a background noise on this side. Professor Dali obtained his PhD in combustion science from the University of Sydney in 1998. The same year, he joined the faculty of the School of Mechanical Engineering at the University of Adelaide and served as its head from 2010 to 2014. He, along with others, established the Center for Energy Technology and was appointed Deputy Director in 2009. He recently joined the faculty of KAUST, where he continues his research in the field of clean energy conversion. For over 25 years, Professor Dali has made important contributions to the research fields of combustion science, aerodynamics, heat transfer, applied optics, CFD, and renewable energy. He has published more than 90 journal papers, and in particular is working on technology solutions to decarbonize heavy industries through integration of renewable sources such as electrification, hydrogen and ammonia combustion, and concentrated solar thermal. I was fortunate to work jointly with Bassam during a short sabbatical at the University of Adelaide, and this fruitful collaboration resulted in the publication of a joint article on solar thermal hybrids for combustion power plants. His strong background in both combustion and solar thermal made it possible to develop innovative concepts and technologies to hybridize these two energy sources for a cost-effective and firm supply of power and industrial process heat. Which brings me to the title of his talk, Hybrid Concentrated Solar Thermal Energy and Combustion for Power and Heat. We are all looking forward to your presentation. Bassam, please go ahead.
Thank you very much, Aldo, for the nice introduction, and it's a pleasure to have you chair the session while I'm speaking. Indeed, this is a topic I've been working on for a while, and will continue to work on in my new role here at KAUST, especially that it is placed with both solar energy and a lot of resources for combustion, and I believe it's actually one of the solutions for the future. So I'd like to acknowledge first the supporting agencies that help to do this work, and my contributors. You had in the previous session from Gusnathan and Alfonso Cinesi, Jen Lim, one of our students, and Ian Samadi, and have Mehdi here online, who also benefited from discussions with him, some of the work that I'm going to present. This is a content of my talk. I'm going to be brief, just introduce the concepts and give new examples where else we can introduce hybridization. So I'll introduce the concept of hybrid solar receiver combustor, and then where else we can do it, and then I help with the concluding remarks. And I'll make a little bit of reference to what Alan has said about how do you counter intermittency. So when we're looking at what's the plan for the future in decarbonizing power and heat, you could see from this figure is that 50% of the energy in the future is going to be from renewable sources, and that immediately says it's intermittent energy, being it the solar, being it the wind, being biomass. That means firm supply can become an issue. Similarly, if we look at the industry, and the same thing, we'll see that 50% of the supplies is going to be from renewable sources, being electrification, being direct heat, and hydrogen, in biomass. So fossils is going to play less than half. Uwe gave an interesting talk about what's high and what's low in terms of energy. So my interest is in high temperatures, which I'm defining as above 400, following what Cedric Felbret 3D put in his 2017 paper, and that's 48% basically of the energy. Almost half of it is a high temperature. It would be fantastic if heat pumps can reach higher temperatures of 500 plus. obviously it makes a lot of sense from the energy perspective, but for now is a lot of energy that would be required for higher temperatures. And there's another work that we published in this paper that Aldo has mentioned, and they're basically looking especially at thermal conversion units. So we were looking at concentrated solar thermal, and we're showing that if you require firm supply, this is basically what industry would require, and you require this much of storage in these 6 areas that you identified in Australia and the US. And I have to say that these areas actually are good solar resource. Here in Saudi Arabia will be actually similar type of solar resource. And you could see here that it's almost prohibitive. The storage is required to guarantee that you're not going to have a backup. So backup means another capex, means another maintenance. It's not just solar. And I just note in here that we're also assuming that the heliostat field is 10 times bigger than the capacity of the plant need to be. So having all of this in mind, then we thought about the hybridization. In the transition, we need firm supply, especially the heavy industry is very conservative, and they want the safety of coming and saying that if there's a problem with the solar system, I could switch to the combustion part. And in hybridizing these 2 options, generally, but I'll zoom into thermal in a minute. Usually what we heard earlier as well in talks about PV and wind and storage, that's really a hybrid, by which when one stops, the other one starts, and also that you have something in reserve. Another one is what we're thinking about, which is renewables and combustion. Combustion we know about and we have been using for many years. It's reliable, it's dispatchable, energy storage is easy, and hence renewable, if it's intermittent, will be supplemented by combustion. Now, these are standalone systems. The cartoon in there shows basically I have a solar tower system alone and I have a boiler alone, and both of them are feeding into the power block. And you know, if you have a boiler, then you have to maintain it running and idle all the time, just in case you need it sometime or during the night. And then during the day, obviously, during the night, I'm sorry, the solar tower need to be maintained hot. Otherwise, in the morning, you're going to lose a lot of thermal mass. The alternative is what we call an integrated system. Maybe you may have heard of concentrated PV and thermal, where basically you do spectrum splitting, so you're having a combined system, or this receiver that has combustion within it, and by which when the sun is not rising, or there's clouds, then you should be able to turn the combustion on and continue operating at constant temperature. And this obviously will have a lot of advantages. So for the considered solar, I don't need really to go through this because previous speakers did a great job in showing you what can be used. But you know, could have temperature processes up to high temperature. You could use it for heat, for power, or for fuel production. But the problem is it's intermittent and variable, of course. With hybridization is we could guarantee that constant output 24/7 using both solar and combustion. And that one complements another. You could have storage if you want to maximize the solar share. And you could cover a lower capital cost because you have one system rather than 2 standalone systems. So we went to actually do some techno-economic analysis of this system that we wanted to build. And we found that there's a lot of benefits from it. It could utilize low flux and intermittent radiation. So for example, if you have a heliostat field and you know that your sky camera knows that there is a cloud coming, detuning your mirrors and retuning them again can take up to 2 hours, depending on the size of the field. Similarly, if you don't do anything, and then the clouds come and then disappear, then you're going to have thermal shock to your receiver, and this obviously can burn it down. And alternatively, actually, the lifetime of these receivers is measured by the number of thermal cycling, and hence capital cost will also increase because you have to replace it more often. Having this combustion system in there, either as Alan mentioned, as electric or as combustion, which can respond much faster, of course, can be a way to actually maintain constant temperature inside and even mitigate this effect which eventually will improve the utilization of the device. It's adaptable, so you could turn it up and down. I mentioned reduced capital cost, and we quantified that for our 30 megawatt thermal systems, where we found that the capital cost can be reduced by about 21%. The levelized cost of electricity, again, by around 20%, depending obviously of where you are. And the fuel, again, on the type of fuel, you could reduce it by 10 to 20%, which basically means you have less CO2, of course. On the right side, I'll show you in a minute, actually a better sketch, but on the right side, there's an experimental system that we built. And on top of it, there's a sketch where it shows where the radiation can go in through the aperture, as well having burners in there to supply the heat. Here's a cross-section of the device we have built. It's 20 kilowatt. We operated in lots of fuels, because this is sort of conference is about combustion as well. So I'm reporting some of the combustion work we've done, both in having combustion as an energy source or solar using this xenon arc lamp at 5 kilowatt electrical. We used air as the heat transfer fluid at atmospheric pressure, and we sectioned the coil inside the heat exchanger into 4 sections, so we'll be able to measure the distribution, each one of them. We ran into this mild combustion, which basically gives you a volumetric reaction and a better distribution of the heat inside. And we measured the temperature and thermal efficiency. We measured the species concentration at the exhaust and also flame stability, depending on all the different fuels that we used, including hydrogen. So this can also be operated on renewable fuels as well. So here's one example of some of these results using natural gas. And you could see in here, on the bottom line, you have the absolute efficiency. Basically, that's for the system. And on the right, you see the power output, basically. And also you see the amount of NOx and CO that we're producing. So with mild combustion, we're able to get really low emissions. And there's a region which is unstable, but you could see in here that introducing, I think this is one of the major questions or research questions we had, does introducing this solar energy into the receiver affects the combustion and its stability. So we found that while the dynamic region in terms of no combustion and mild combustion remains roughly the same, but we have a shift in the amount of energy extracted if we run it in what we call the hybrid mode, which is solar and combustion at the same time. And we could see here on the bottom what sort of absolute efficiency we found, and we're between 28% and 47%. Remember, this is not fully optimized. We're only using pressurized air, which is not the best heat transfer fluid, and but it's giving us reasonable results. Well, what happens if we sort of blend it with a little bit of hydrogen? Would that improve it? And obviously, the stability of the flame increases with it. The absolute efficiency increases. So now on the left, you have the percentage of hydrogen, on the y-axis. On the x-axis, you have the absolute efficiency. And on the right side in these boxes, you could see that we could reach up to 81%, basically absolute efficiency at 100% hydrogen. So theoretically, you could run it on hydrogen. And by the way, we were having mild combustion at hydrogen, and you could see that the NOx emission remained relatively low. So again, the dynamic region still observed, but that the hydrogen addition increased stability, and hence with it the efficiency as well, as I showed you on the bottom. In terms of NOx emission, I think just look at the maximum of the both y-axis, and you could see that it's really low. So we were able to operate the systems at relatively low emission characteristics, both in combustion only and a mixed mode. So so adding the radiation into the flame did not affect the emission. If you look at the thermal efficiency of the system, and I have to say here that we have accounted for heat recovery using the normal method. And you could see that, again, the combustion only, the mixed mode, and the solar only, giving us roughly the same thermal efficiency at different sort of heat flow rate of, up to 90+%. And you could see here in terms of the maximum heat transfer fluid temperature, we were able to reach sort of around 780 or thereabout. using is as well syngas. So we tried syngas at different ratios as well. So with this efficiency and these temperatures, we found that this concept actually have some legs, both for heat transfer, for heat generation of thermal energy, and in certain niche markets for perhaps electricity generation as well. So where else we can hybridize? So since then, we also looked at different aspects where we can hybridize. Here's one idea. Comminution, which is basically the crushing and grinding of the rocks in mining, costs between 30 to 40% of the energy. And remember, most of those are in remote mines, so the cost is expensive because you have to truck diesel all the way there. It's mostly obviously electrical energy because you need the grinding machine in there. So what we found, it's well established that removing the bonded water in these ores reduce the grinding energy by 50%. So, but in the past, they tried two things. One is convective heating. Another one is plasma, a microwave. And both of those had trouble. Convective heating takes a long time, is not efficient. And microwave scaling wasn't sort of available and wasn't as efficient. So this time what we tried is basically high heat flux. What we were simulating is concentrating solar energy into these ore particles and seeing if we actually are able to what's called dehydroxylize, in other words, removing this bonded water from this ore in a cost-effective one. And you could see on the bottom there, there's a figure showing exposure time and showing sort of what we call D80, basically percentage of the 80% of the ores sort of reach a particular size. And you could see that we could heat this particle, depending on the maximum temperature, up to 800 degrees C within basically less than half a minute. In fact, our theoretical calculation shows the temperature can be in 3 to 5 seconds if you have small particles that will reach this temperature. This has an advantage that the structure, the morphology of the ores remains the same, and only the water is actually released. So we've done some calculations and we found that if you recover some of this heat from the ores, that you will be ahead by almost 40%. So there's value in doing that. And where the hybridization aspect of it is, instead of using solar only, you could actually use other electric radiation, or you could use radiant burners as this experiment shows in here, where we sort of subjecting the particles into radiation. So further research is needed in here. We need to identify suitable ores that can benefit. So this was tried on nickel, and the benefits there are substantial. In softer ores, it doesn't work well, but in tough ores, actually, it is a very useful technique. We need to look at, obviously, how much we're going to save depending on the ore, and look at techno-economics for greenfields and retrofitting if this idea actually has legs. But our calculations showing great promise. This work was supported by BHP, and the work in Adelaide is continuing, and I'm also doing some work here in Saudi Arabia on the same concept. Second one is hybridizing the supercritical CO2 cycle. As you know, the cycle is quite efficient. There is demonstrated cycles of around 52%. Theoretically, you could reach much higher levels. My concept is to hybridize this in two ways, either to do reforming of methane into syngas, and here I'm talking about more dry reforming, or do direct heating of CO2 through sort of a tower system. As you know, with the supercritical CO2, 90% of the working fluid is actually CO2 itself that has been recovered, and hence any way by which we could heat it again at high pressure, then that would actually give us the cycle efficiency that we require. There's some work that's been done theoretically showing that if you do steam reforming, you actually can save 11% on the fuel consumption without energy storage, so you could maximize that as well. So research here is how do you integrate dry reforming into the alarm cycle or alarm FedVet cycle. I want to look at the development of a windowless solar receiver to try and basically heat up the CO2 to the temperature required. I'm also working with the 1414 in Adelaide to look at high temperature, high pressure thermal storage, including with electric heating to basically support the cycle. So if you have excess PV, this perhaps is one way to store it such that you'll be able then to recover the energy in a high efficiency, especially when battery is too expensive. And we want to look at system level dynamics and modeling. And also, I'm looking to build a small system in here. The good thing about solar supercritical CO2 cycle is that the efficiency is quite high even at low capacity. The last one is the steam calcination limestone. It's a project which started in Adelaide and continuing. I won't go a lot through the details, but there's a Aspen model that we did. You could actually split water and then reburn hydrogen and oxygen, and you could recover 93% of the water and capture almost 98% of the CO2. We've done some techno-economic analysis, and Mehdi is involved in this project. Is that compared with natural gas combustion plus capture, this approach will be viable at $2.50 a kilogram of hydrogen, and we're heading there quite fast. So this, I believe, this concept has legs, mostly because in the exhaust now you're going to have CO2 and water. You're going to return the water and capture the CO2 quite easily. So this is other research questions. I won't go through them in details, but there's another concept also of using hydrogen peroxide. And again, Mehdi is doing some interesting work in there, and we're looking to publish this in the near future. So let me just finish by concluding this, that direct or indirect hybridization is needed to facilitate renewable energy penetration and deliver affordable firm supply, in our view, especially for heavy industry. Direct integration, integrated hybrids offers tangible benefits in certain applications and give industry the certainty it needs. There are many opportunities to decarbonize industry using CST and combustion beyond power. So heat obviously is one of them, and the other two examples I showed you are another interesting ones. And the R&D is still needed to do system integrations. I think that that's becoming quite critical, where we actually can take this into that and integrate them together to get the maximum profit. And thank you for your attention.
Thank you, Bassam, for this presentation of hybridization of solar and combustion in a solar receiver. This is a new territory with very high potential, and I'm sure there will be questions following up later on. We are now coming to the last presentation, and it's a pleasure for me to introduce the next speaker because I happen to know him very well. I'm very fortunate that he's a member of my group. This is Dr. Emiliano Casati from the Department of Mechanical and Process Engineering at ETH Zurich. Emiliano received his PhD degree from Delft University of Technology, the Netherlands, in 2014, conducting research on advanced energy conversion systems with focus on organic Rankine cycles. He was a Marie Curie Fellow from 2017 to 2020 and leader of a project leading with high temperature thermal storage of concentrated solar energy using molten glass. At ETH, Emiliano is a senior research associate and lecturer. He teaches the graduate level course, Renewable Energy Technologies, which happens to be a very popular course with attendance of over 230 students from several departments. Emiliano, a pleasure to hear your talk. The title, High Temperature Thermal Energy Storage.
Thank you, Aldo, for your kind introduction. Can you see my slides?
Yes, we can see.
Okay, good. So I can go. Hi, everyone. So here is the presentation structure. I will go through a quick introduction, then classifications of storage concepts. And then state of the art, this will be the focus of my talk, and then something about current developments, mainly literature references, and then some conclusions. First of all, I would like to clarify the approach of this talk. I want to put thermal energy storage R&D into context, and to do this, I want to focus on concepts which actually made it to real application. So this is why I will focus on where do we stand in terms of state of the art of high temperature thermal energy storage. I put a lot of materials in the slide. I will not have the time to present everything, but I hope you will have the interest to go through it in case you are interested, and in case you can contact me. First of all, the role of energy storage in general, we heard many times during the talks of today that this is needed to actually bridge fluctuations, especially when dealing with renewables. And as of today, we have a niche for thermal energy storage. Most of the storage, new capacity is still in form of hydro storage or battery storage. But for large scale systems, as we are interested in, this is not economic at the moment. So thermal energy storage is still a kind of a niche market, but there is a big but, as you know, because the role of thermal energy is paramount. So we have approximately 1/3 of final energy consumption in the form of heat, and most of it is going into process industry. So I just listed here the few processes happening at temperatures larger than 1,000 degrees. And these also have a huge impact in terms of global greenhouse emissions. So how do we classify thermal energy storages? There are different ways, but first let's go through some general concepts. First of all, the capacity. So we define the capacity in terms of equivalent hours. So the hours of nominal operations allowed by the exploitation of the storage only. And another important concept is the efficiency. We usually talk about round trip efficiency, so considering charging, idling, and discharging phases, and also accounting for thermal degradation. So especially at high temperature, especially if the conversion is from solar to chemical energy or from solar to electricity, is important to account for the exergy of the storage. So if we load at 1,000 degrees and we discharge at 700 degrees, we may not lose a lot in terms of energy content, but we lose a lot in terms of exergy content. So this is important. Let's go into the classification of storage. We know we can classify storages in terms of storage principle, and here we have the three main families of tests, which are sensible, latent, and thermochemical tests. And you know there is a strong trend going from sensible to thermochemical of increasing energy density and decreasing industrial development. And this will be clarified also in the following. Sensible test is storing energy by raising the temperature of a material, which comes with a variable temperature upon discharge. The energy densities are relatively low, but also the costs. And as I will explain in the following, this kind of test is the only one who actually made it to the market in a way. Then we have latent tests where storage exploits a phase change, and the great advantage here is that we can have a constant temperature of discharge, and this is important, for instance, if we want to run a chemical reaction. Finally, we have thermochemical tests with the highest theoretical, I would say, storage densities, but also with the least development and many technical complexities and projected high costs. Another classification follows the storage integration scheme. And here the message I would like to convey is that the TESS integration is paramount. So we cannot think about a TESS without thinking about its integration in the process for a number of reasons. There are just few ways we can integrate tests in the system, and these are listed here in this table. Here is from IRENA, a table reporting some general costs and market share, for instance, for the 3 different types of storages. And you see the cost is increasing dramatically, going from sensible to latent and thermochemical. But I would like to stress that these are even like projected costs, because as I said, there are no real large-scale implementations of these type of storages. And the same applies to market share, which is still negligible for these other ways of storing. So what's the state of the art of high temperature thermal energy storage? First of all, I try to identify the markets. And these are the market of CSP, so concentrated solar power, which is actually the most established one. And many concepts are first applied in CSP. So this is really like the reference. Then we have a somehow growing field of industrial waste heat recovery at high temperature. And then we have an emerging field of what is called power heat power, which is actually gaining interest due to the need of absorbing intermittent generation from renewables, mainly PV and wind energy. However, again, I would like to stress that we only have sensible thermal energy solutions applied so far. So let's go a bit more in detail into sensible tests. We are storing by raising temperature of a material, so we can generally express the storage capacity in terms of energy per kilogram of material, for instance, according to this kind of formulas. And of course, we would like to have materials which are as cheap as possible on a mass basis, with a specific heat capacity as high as possible, as large as possible, and also, of course, the temperature of the delta T of the process should be as large as possible. But this is, of course, has to be considered together with the process. Then we have other further desirable properties. Here I listed in this table the sensible test materials which were actually employed in commercial applications. We have oils, or in this case we have oil with sand and rocks, so in a dual media storage. And then we have solar salt or molten salts that, as I will explain, this is like the state of the art. And then we have solid materials like concrete, fire bricks, and rocks. Here I listed the typical temperature range of utilization, which is of course important when we talk about sensible storage and other properties. In particular, this one is the cost of the energy stored considering the material only. So dollars of material per kilowatt hour of thermal energy stored. What kind of systems do we have now working on the field? We have steam storage. So according to this scheme of integration, steam is produced in the receiver, solar receiver, and directly stored. I won't spend too many words here. There is a long history. These systems have been working in the industry since decades. The problem is that the temperature is rather limited because of the use of water, and the main issue is that we need high pressure containment. So the costs are rapidly growing with capacity, and these are usually used as buffer storages. So for storage periods lower than 1 hour, 1 hour usually. Then we have thermal oils. Again, this was one of the first concept considered in the 70s with the direct storage of oil. So oil was used as a heat transfer fluid and also the storage medium. Accordingly, we can obtain a rather simple layout. However, temperatures are also limited, and above all, these fluids are expensive. and flammable. So basically all the systems storing directly thermal oils sooner or later had some fire problems, so to say. So this is actually not used anymore as a concept. But now, currently, oils are used in parabolic trough systems to as heat transfer fluid according to this indirect storage integration, where the energy storage is done is accomplished with a 2-tank system using molten salts. Of course, in this case, molten salts are somehow underexploited given the low temperature, because the use of oils implies the temperature, a rather low temperature of below 390 degrees Celsius. However, this is one of the layouts which are still built today. So this is one of the two actually. This is an example of a recent large system, 250 megawatt electric, which exploits this indirect concept. You see, these are the molten salt tanks. You see here dimensions and also how many tanks are needed. Then we have molten salts, which I would say are actually the state of the art, and these work with the tower CSP technology. So molten salt is directly circulated into the receiver, heated up and stored. So we have this kind of integration. So it's a direct active storage system. Molten salts have the nice properties of having low vapor pressure at high temperature. And you see the layout is rather simple. However, the fluid handling is not so simple because basically because of freezing temperature of salts around 200 degrees. So we need to heat trace, and also we need a gas protection system. Also, in this case, we have a technology which is now becoming, I would say, the leading CSP technology. But still, I would like to stress the fact that the development started some 30 years ago or more, and even before, because molten salts were considered for nuclear applications since the 50s. So you see, there is always a long time before something gets to the market, and this is mainly related with the high investments required to build these systems and with the relative bankability issues. Again, here is a case of such a direct molten salt towers. This is the Gema Solar Tower in Spain, which is the first commercial implementation of the concept I've shown. And here I reported some data for you to go through. What is the state of the art? I just went through the databases available, and in the last 5 years, we had 22 CSP systems coming online, 19 of these with storage, only 2 with steam accumulators, so buffer storage. All the other, so 17 systems, are implementing a 2-tank molten salt test systems. So for, up to now, we still have almost an equal share of between indirect parabolic trough collectors or direct tower systems. So it's still half and half, but tower systems are moving to the forefront, I would say. Beside the CSP field, we have other use of thermal energy or sensible thermal energy storages in waste heat recovery applications, and these are again established and used since decades. This is a modern glass furnace. You see where you have this heat recovery system based on fire bricks, similar to the copper stove, which was patented in the 19th century. And the idea is to recover heat internally to the process. More recently, there are concepts being proposed to recover, for instance, from off-gas systems of steel factories. So this is a concept developed by Siemens to use molten salts again to recover heat from a steel factory. And here you have some more references. Finally, we have what I call power to heat to power applications, which are gaining interest to avoid the renewables curtailment or to exploit periods of low electricity prices. And this, you see, is a large prototype by Siemens Gamesa, commissioned a couple of years ago in Germany. And the idea is to basically have a fixed bed of rocks, which are heated up by air, and then it is reconverted into electricity through a normal Rankine cycle. As you can imagine, the efficiency is, the round trip efficiency will not be so high, but still it makes sense from a techno-economical point of view. About current developments, I will be very quick. We have a new concept for sensible thermal energy storage. I listed here all the references. And what I find particularly interesting is to look into known materials for which high temperature experience exists. And this is what we did at ETH by looking into glass, because molten glass is handled since thousands of years and containment is not an issue. So we took amber glass recycled in the order of kilograms, so not micrograms. We put it in the solar simulator into a crucible, and we melted it by directly absorbing solar radiation into the glass. We were able to reach temperatures of 1500 Celsius and maintaining them for around 10 hours, obtaining having no problem with the containment. This is the crucible cut out after testing. And we are still going on with this kind of research. Then the last two slides, I will not go through them, but I listed some references for latent tests development at high temperature and thermochemical test development at high temperature. As I said, none of these concepts made it to the market, notwithstanding the fact that we are studying them since the 70s. So my conclusions are as follows. Of course, it's a personal view. We should, I think, aim at developing test concepts which are deployable in few years and should survive more than 20 years in harsh environments. Remember about Murphy's Law. So about R&D on new materials and concept, I think we should aim at improving significantly over the state of the art. We should focus on safe and non-toxic materials only, in my opinion. And of course, materials with low cost and favorable properties. Also important is that we should demonstrate stability, so cyclability of materials since the very beginning. So when we publish something, we should already demonstrate that the cyclability is reasonable. So these are my conclusions. And with this, I would like to finish my presentation. To thank you and to, of course, open the floor, since I'm the last one, open the floor to questions.
Thank you, Emiliano, for the presentation. And we have concluded the 5 presentations of this, and now we go into the panel discussion. I ask all the speakers to activate their cameras so we can see each other, and also the participants can see you. And I'm not sure how we proceed at this point from the logistic point of view, but somehow is it we open the floor for questions, and whoever wants to ask a question, raise the hand. Is this the way to proceed?
Yeah, well, in the Q&A in front of you, I'll do this some questions, and you could ask questions ourselves or somebody here in the audience. We haven't got many now here, but
okay.
Last I looked, there's around 80 people online. So
very good. I see a few questions in the Q&A, but I prefer that the participants, they ask directly this question, and then they can address a specific panel.
Okay. Well, they need to identify themselves so we could put their audio on, because it's a webinar, not a sort of a direct Zoom. But you could also read the questions themselves if you want. But I have a question, if I can, to Emiliano. Very interesting talk, Emiliano. I think the material you presented is really valuable. So one of the issues, I was talking about the supercritical CO2 cycle, and there's a need to have the CO2 at a high pressure, or when it's recycled, it's already at a high pressure. And do you have any ideas or ways by which, or what's been done in the literature in accommodating some storage to actually continue the cycle going from stored energy?
So you mean high pressure storage for CO2 cycles, or high pressure storage in general?
Well, one issue is that obviously you want to well, both of them perhaps, I'll say.
Well, in my opinion, there have been few studies about high pressure thermal energy storages. One that I am aware of is was intended to be coupled with supercritical CO2 systems, but the problem there is always the cost of containment at high pressure explodes with size. So actually, I think it is conceivable to have a buffer storage, but it's not conceivable to have a multi-hour, storage for 100 or more bars. So that's, I think, a bit the idea. I don't know if this is answering your question.
Thank you, Bassam, and thank you, Emiliano. Let's move to the next question. And please raise your hand if you have a question, and your microphone
Anybody
is
online?
unmuted.
Oh, well, we'll let you know, Aldo, if there's somebody putting their hand up, but maybe in the interim, you just lead the discussion if you want to.
Okay, then if there is no hand raised, then I can read from the question. By the way, there is an echo, and I think this has to do with your microphone, Bassam.
Yeah, okay.
Can you mute your microphone? Let me see if we still have this echo. Okay, so let me read from the question and answer. There is a question. I guess there is a question that is addressed to Mehdi. The question is, would an hydrogen sulfide cycle work with H2S instead of H2SO4?
I think the point that sulfuric acid is used is that it has both hydrogen and oxygen, and when you heat it up to high temperatures, it dissociates into oxygen and sulfur dioxide. But if we heat hydrogen H2S, hydrogen sulfide, I reckon, to high temperatures, it dissociates into H2S, into sulfur and oxygen, hydrogen. And to close the loop, we need another step or another reaction to add hydrogen to it from another source. I think maybe with the same process, it wouldn't be possible, but if we can find another material to close the loop, maybe it works.
Okay, thank you, Mehdi. Let me move to the next question. There is one from Jalil Sulkarnain. And I guess this question is being addressed to Alzheimer, because the question is, what about using hydrogen for energy storage? And can be involved in thermal energy. So basically hydrogen generation for not as a fuel, but for energy storage purposes, if I understand correctly this question. For thermal energy storage.
Yeah, I think so. I think that might be difficult because of the fact that it's a gas and low density. However, you know, if you could convert that to a liquid, it's sort of like a fuel, as you're saying, like not do that. But if you were to convert that to a fuel, for example, if you also split CO2, you could get to a liquid fuel, which would be a very outstanding energy storage medium.
Okay, let me follow with a question to you, Al. And this is about the last slide that you presented, the path forward. There, one of your bullets addresses the issue of inner gas because it's an energy expensive gas. And I wanted to ask you whether using instead vacuum pressures during the reduction process can improve the energy balance instead of using an inner gas.
So yeah, so what you're asking is, can vacuum pumping be used as an alternative to remove oxygen relative to flowing inert gas? So I'm sure, I think it can. It depends upon the efficiency and the cost of the vacuum pumping and how much improvement can be done on that. Because I think with the existing processes, those efficiencies are very low in order to get the oxygen content down to where you would need it in order to be able to carry out the redox chemistry. But sure, it could certainly be used. It may be somewhat slower than flowing gas, right? To pull, to be able to carry out a vacuum and pull off the oxygen, but it could certainly be done.
Okay, thank you. Next question from one of the participants. I assume this question is for Bassam, but I'm not sure. It says, could concentrated solar thermal be used as a capture, as a CO2 capture technology for splitting capture CO2? And I thought that this is for you, Bassam, because you address this process where you can capture CO2 from the cement manufacturing.
Yeah, thank you, Aldo. I mean, other than through the chemical looping process that Mehdi has described in a little bit, I can't see how so it's directly can be used. What I was showing is that basically through steam reform, steam calcination, you can recover the CO2 or at least capture it much more efficiently because you don't have the nitrogen in there, and separating the steam and the CO2 is not expensive. So beyond that, I think it's mostly chemical looping process where, you know, through, as you know, redox process, you actually can separate the CO2 from the rest of it. But directly, I don't think it's viable at all. There's no other options.
Thank you, Bassam. Let me follow with a brief question to you. You presented this very innovative design of a solar receiver where you have the hybridization of solar and combustion. And my question is a, I would say, a general one. What are the challenges in operating this solar receiver?
Thank you, Aldo. In fact, so one of the challenges is that you're trying to match two heat transfer modes, one through convection, one through radiation, of course. So what we ended up doing actually in, I guess, model 2 of this receiver is instead of having this mild combustion filling up the volume, we replaced that with radiant burners. So basically now both sources of energy are coming through radiation heat transfer. And we have done some trials in them, but we haven't sort of developed it to the same level as the one I have shown. And there we were able to reduce the length to diameter ratio to be favorable for the solar as well, which is around 1. While what I showed you could see that it's 3 to 1. It's actually quite a long receiver, which is not really favorable for solar radiation. So potentially this is where the issue is. One other thing is hotspots that we need to handle. And we have some ideas how to resolve that, get a little bit more uniform temperature. But, and obviously cost and limitation of a cavity receiver, which is normal for some of these systems. We don't think we could build a system more than theoretically 10, 15 megawatt. If you want to go to 30, it's going to be a bit of a stretch. One other thing perhaps that we actually done some work on was reducing the convective heat transfer from the aperture. And for that, we came up with an idea of aerodynamic means to basically run some air jets close to the aperture and use some of this air as part of the combustion air. So this way, then it's incorporated at the same time. It's a small penalty in terms of cold air coming in, but in fact, we could also recycle the exhaust as well. So there's ways by which you could minimize convective losses as well. That was another challenge. Okay, thank you, Bassam. Perhaps to the participants, you can raise your hand, and then your microphone will be unmuted, and then you can ask the question. I cannot see the participants, but if you have a question, you can ask directly. In the meantime, let me look at the panel of question and answer. But I have a question to Professor Uwe Riedel. You discussed the generation of e-fuels, no, by means of electricity, and I wanted to ask you, how have you done a comparison between thermochemical production vis-a-vis electrolysis, the electrolytic production of fuels?
I'm not sure I got the question right. So working with e-fuels for certain applications like aviations, which I was talking about in the earlier KAUST workshop, they require a stable and safe liquid hydrocarbon in contrast to hydrogen. When we talk about industrial processes, I see hydrogen to be used more than e-fuels, because e-fuels are simply too precious, because hydrogen is sort of the precursor for all the e-fuels.
Let me rephrase my question. Sorry, I was the way I asked was confusing. I was referring to the manufacturing of these fuels. For example, for aviation, kerosene for aviation, there is the electrolysis path and there is the thermochemical path. Have you done any study comparing these two approaches to e-fuels for aviation?
I mean, so I'm still not sure I got the question right. So hydrogen is the first.
Yeah.
No worries. In aviation, we have certified paths on how to get to fuels, and up to now we have seven different paths to the aviation fuels, and of course we have made comparisons, and none of the new pathways can compete with fossil fuel, fossil crude oil based jet fuel.
Okay. Well, I don't want to extend the discussion, but I wanted to see a comparison between PV, solar PV or solar CFT for electricity generation plus electrolysis plus the reverse water gas shift all the way to kerosene.
Yeah. Okay.
Vis-a-vis.
Yeah, no, okay. Yeah. Okay. Yeah. We have not done that in detail so far, but it's ongoing research at other DLR institutes. We have a project coming to a close in about 1 year, and there will be an extensive report and comparison on all the options how you get to green jet fuel.
Yeah. Al, you in one of your slides you were mentioning PV electrolysis of water. This is competing vis-a-vis the solar thermochemical water splitting. Do you want to add to this discussion?
I mean, yeah,
go ahead.
Yeah, the way sorry, keep going.
Yeah. Al, please go ahead.
Yeah, no, I mean, PV electrolysis is the renewable target, right? That's like, forget methane, forget carbon fuels and things. Really, in the carbon-free, reduced carbon era, you need to beat PV electrolysis. And I think the opportunity for redox processing, if you can avoid intermittencies, somehow within a cavity, and also if you can run at pressure, right? I think you have to be able to run the oxidation step at pressure to avoid downstream compression costs in those applications. Hydrogen has to be compressed up to very, very high pressure to go into a fuel cell vehicle. Pipeline pressure is about 300 psig or more, 25, 30 bar. And so I think in order to avoid the cost of that compression, if you can, basically pressurize water with a pump and be able to operate that system at pressure, that's a huge advantage. And I think also, I think the recuperation of heat, I don't know how you do that. PV doesn't have that opportunity. And so I think that that there's huge opportunity for also heat recuperation in the process. So I do think it's going to be a tough, very, very tough choice there, but it is possible, except PV electrolysis is far ahead because it can be implemented today. But I think if you also look at making syngas and you want to make liquid fuels, I think at that point, the opportunity is cracking CO2 and water simultaneously to get to the right syngas composition. And the competition for that is PV electrolysis, and then that hydrogen feeding a reverse water gas shift reactor to get to the syngas. And reverse water gas shift is not that easy. And so you're looking at two process steps versus one. And I think in the case of manufacturing liquid fuels, that clearly the redox processing, especially if you can provide that second step at pressure, does provide a huge opportunity in order to supply sustainable liquid fuels with captured CO2.
Thank you, Al. And thanks for pointing to this, to the reverse water gas shift that appears to be the bottleneck for the e-fuel path to hydrocarbons. And in the thermochemical approach, you don't need to perform the reverse water gas shift reaction. I see a question that perhaps this is for Emiliano. Let me read it, although I'm not sure if I understand this question. Is from the Horas, and it says, what are the capacities and timescales of the sensible heat-based systems, since their Carnot efficiency, exergy, drops during discharge?
Well, let's see what I can do to answer this. So timescales for sensible heat are for real systems, for molten salt systems are of the order of days. Potentially can be larger, but of course the limitation is heat losses. which is degrading the energy, the energy because the temperature is dropping with time, and that's of course more influential for small storages. So for state-of-the-art systems with these huge storages, actually the temperature drop over a few days is negligible. It's like maybe 1 degree every 3 days or something like this, really very low. Of course, then the point is also is just a techno-economical optimization of how much insulation you want to put and these kind of things. About exergy loss, for sure, having a sliding temperature, so to say, it's causing the exergy potential to be reduced. But here the important point is always, let's say, what is the exergy that you extract with respect to the exergy that you put into the storage. So in the end, that's what counts. And I mean, I have no numbers out of my head, but as I said, in this, when the storage is used as normal it is within, let's say, a time frame of days, the exergy efficiency is above 90%, something like this. The DOE, the Department of Energy, set some benchmark values within the Sunshot program, and that was I think 95%. So this exergy, round trip exergy efficiency. So these are the numbers we are talking about. But again, we are at 500 degrees so far. We are not yet at the temperature levels needed for thermochemical reactions, unfortunately.
Thank you, Emiliano. Any hands have been raised? I cannot see that from my side. Once again, participants who would like to ask questions, you can do that directly by raising your hand.
Yeah, I couldn't see any, Aldo, but I have a question to Mehdi. If they've done any cost estimates of hydrogen using this high cycle, especially the solarized version of it.
Sorry, Wissam, what was the question? The cost of high cycle?
The cost of hydrogen using the high cycle with solar.
Based on previous assessments, I think it's around $5. But if we can improve the performance in reactors, it can go down further, definitely. I think it's based on previous assessments, it's around $5.
$5 per kilogram. What is
kilogram? I have better numbers here. Maybe just give me 1 sec. It's around, yes, for like a capacity of 100 tons of hydrogen a day, it's around $5 US, it's Australian dollars per kilogram.
Maybe I have a question to you now that you are in the microphone. What is the status of the solar bubble reactor? Have you built a prototype? Have you performed some experimental runs? Can you share some of the results?
Actually, we have run some experiments on the non-reacting environments with argon and gallium, and I showed some of the results and a paper published in Solar Energy. But we are also looking at other configurations, because like indirectly heated systems that we can use, like particles or other kind of heat transfer medium to heat the system. So we have developed a couple of other configurations. We have tested in cold prototype, not yet in hot prototype, but we are planning to do that as well.
Okay. Thank you, Mehdi.
No problem.
We still have a few more minutes. How are we doing with the time, Bassam? Because we started.
Well, we were just on time. We're done.
Okay, so let me perhaps finish with the question to each one of the speakers. Each one of you is working on different topics. They have in common is the input of renewable energy and in particular concentrated solar energy. And I want you to project yourself 10 years from now. We are in the year 2031. And I want you very briefly, it's important that you give me a brief answer, to tell me what is the status of your technology, the technology that you are developing in the year 2031. And let me start, let's go by the order of the presentations. Al, your thermochemical cycle with arsenide and the solar reactor configuration that you showed today. Where are we in the year 2031?
So, normally what I would have said was that, there was no way that we would actually see this in practice, okay, anytime that soon. However, in the United States, there's been a huge resurgence in clean carbon, and the state of California has huge incentives for renewable hydrogen and replacing natural gas and all kinds of things, fuel cell vehicles. And so to some extent, and I say this not necessarily so lightly, but it's almost like there's more money out there than good ideas. And so I think it's possible that you would see this process for the production of hydrogen in a smaller tower system, maybe distributed for fueling stations or something, with something like the hybrid receiver involved in that. I also think it may be possible to look at liquid fuels. These oil companies, the energy companies, are sort of being left out, and they're being sort of stepped on, like, we need to get them out of oil. And they're the ones who actually have a lot of money to spend on renewables and a lot of interest in using hydrogen. And even though we don't hear too much about liquid fuels, right, we're all going to go with battery cars and everything. I think there's a huge opportunity with some of these major players, Shell, ExxonMobil, Chevron, Total. I can see opportunities for them using captured CO2 and water and getting to diesel or gasoline. And so we can't write that off, especially with what's happening in the Netherlands, right? A lot of pressure on Shell right now. And so I think there's a huge opportunity in that regard that people are not paying attention to.
Thank you, Al. Same question to Mehdi. Please be brief. Where are you with your technology, the solar bubble reactor and the upper production in 10 years from now?
Yeah, I would say that, in Australia especially, there is potential for that technology, and there is a strong interest from industry. We have BHP, which is committed to decarbonize by 2050. And as I said, most of the systems or most of the mines in Australia are located in remote areas. So they are looking for technologies that can supply hydrogen and oxygen. And I think in 10 years, there is great potential that we can, demonstrate at pilot scale or do some on-site tests with some demonstration at bigger scale. Also, I think in near future we will have carbon tax in place, and then that would also help, pushing these technologies forward into the market and make them more competitive with other technologies.
Thank you, Mehdi. Same question to Uwe Riedel in the context of electrification for the decarbonizing the industrial processes. Where are we in 10 years from now?
All right. I believe that with our new heat pump technology, we will have reached the 600 degrees Celsius. And this is a range useful for several industries: food, paper, printing, rubber, and plastics. So 600 is the target.
Thank you, Uwe, also for the brief answer. And same question to Bassam in the context of hybridization between solar and combustion. Where are we 10 years from now?
I believe actually we're going to have pilot plants operating. We have here in Saudi Arabia the biggest oil company in the world, and they're also keen to do something. They don't want to give up oil too easily, obviously, but they want to enter the new markets. There's an excellent resource in terms of solar, and also there are many remote mines as well, which require both energy and decarbonization. So I believe that there will be systems to point to at a scale which is respectable, and I do agree with Alan that there's a lot of money for smart ideas these days.
Thank you, Bassam. Last but not least, Emiliano, in the topic of high temperature thermal energy storage.
Yeah, well, I think we already have concepts out there. I think we will have improvements for sure. What I would like to stress again is the importance of working in, let's say, from the R&D point of view, working on things which are, you know, potential to get to the market in 10 years, because it looks a long time, but is not. So we should study stuff with a huge potential. So not improving 50 degrees, but improving 300 degrees and deployable in few years, because time flies.
Thank you, Emiliano. At this point, we are concluding this session. I would like to thank all 5 speakers for your presentations and for the panel discussions, and thank the participants for attending. And I give the word back to Bassam for the closing remarks. Thank you.
Thank you, Aldo, for doing such a stellar job in leading us through this session. And thank you all for your really valuable contributions. I enjoyed the session, and I'm sure many others online have as well. So this actually concludes this conference as well, which has been quite an exciting 3 days. The title has the word combustion in it, although we've shown that integration and another means of thermal energy is possible through this process. So for that, I'm also excited is that the future looking promising as well. So with that, I'd like to thank all the participants. We had more than 750 people registered online over the three days. We're excited about how interested people are in these topics that we discussed. And with this, I will finish. But we're going to play a short video. Those who missed it or still online may want to see it. It's a virtual tour of our labs. We played it during the break, and we'll play it again. But stay all safe, and thank you again for your contribution.
Thank you. Thank you.
In the Advanced Laser Diagnostic Lab, we develop novel strategies to overcome existing limitations of combustion diagnostics. The corrugated picosecond Raman spectroscopy temporally separates the Raman signal from soot incandescence and laser-induced fluorescence, enabling interference-free Raman measurements in mildly sooting flames. The Hydra, our hyperspectral 2D Raman analyzer, allows 2D Raman measurements of temperature in major species in high-pressure, non-sooting methane air flames. It also allows for high-precision 1D Raman measurements at 10 kHz. We have extended interferometric Rayleigh scattering velocimetry from point-to-line measurements with our novel design based on a virtually imaged phased array. The diagnostics will be employed to study combustion in small channels and supersonic combustion. In the Combustion and Pyrolysis Chemistry Laboratory, the gasification and pyrolysis of different residues such as biomass and heavy residues from crude oil are investigated. fractions from various feedstocks can be separated and investigated independently in our different reactor facilities under fixed temperature, pressure, and residence time conditions. In addition, we perform high-fidelity numerical simulations using quantum chemistry, kinetic rate calculations, and molecular dynamics to understand oxidation and pyrolysis in reactive environments. For gas phase systems, we conduct experiments in flames and jet-stirred reactors to understand chemical reaction mechanisms and determine associated thermokinetic parameters related to oxidation of different types of fuels. In addition, we have special reactors for studying catalysis under heterogeneous gas-solid environments. In this lab, we measure the electric field of plasma-assisted flames by a laser technique called EFISH, for electric field-induced second harmonic generation. A methane air flame is ignited in a stagnation flow burner. This flame can be seen here with and without plasma. To measure the electric field, an infrared laser is focused on the flame region, a part of which will be changed into a green beam. The beam's intensity is proportional to the laser irradiance and the electric field squared. This technique can measure the electric field during plasma actuation of the flame, which is crucial for the understanding of plasma chemistry. Welcome to Building 7, our high-hazard H5 classification lab space, where we house most of the larger scale projects. KAUST was built to Saudi Aramco standards for petrochemical plants. The sophistication of the toxic gas management system is clearly evident on the walls in this corridor. The lab is capable of providing 0.5 kilograms per second of airflow at 45 bar continuously, plus an extensive fuel delivery capability including hydrogen, methane, ammonia, and various liquid fuels. The high bay area, with a ceiling of 12 meters, contains several large, high-pressure experiments. The centerpiece is the high-pressure combustion duct, the center's workhorse for studying canonical flames at pressures relevant to gas turbines and internal combustion engines. Here you see a high-pressure ammonia swirl flame and a part of the laser-based diagnostics being developed to measure a wide range of major and minor species. Also in this lab is the heterogeneous auto-ignition rig, designed to study the combination of chemical and physical delay in the auto-ignition of real fuels at pressure. This lab also contains the pressure gain combustion rig. This rig is used to investigate an alternative to constant pressure heat addition in gas turbines using constant volume heat addition. This isochoric heat addition results in an increase in stagnation pressure and hence thermodynamic efficiency. We are investigating acoustically resonant deflagration waves using either passive or active valving to demonstrate pressure gain combustion at elevated initial pressures. With the growing interest in hydrogen and ammonia, We are investigating the feasibility of converting a conventional natural gas-fired microgas turbine to an ammonia, hydrogen, or ammonia natural gas-fired gas turbine, measuring both the performance and emissions from a commercial device. In this lab, we have two experiments, the new very high-pressure constant volume combustion spray rig and the turbulent flame speed rig. The spray rig is designed to handle pressures up to 300 bar to investigate next-generation isobaric combustion using a pre-burn to generate the necessary temperatures. This vessel will also be used to investigate supercritical carbon dioxide oxy-fuel combustion at pressures relevant to the alum cycle. Note both of these rigs take advantage of the blast-proof control room and can be operated from this room for safety. The second experiment allows for the investigation of chemistry turbulence interactions by measuring turbulent burning velocities at various initial pressures, temperatures, and turbulence intensities. The isotropic turbulence intensity can be controlled via 4 high-speed fans. Using Schlerin imaging, the expanding combustion wavefront can be measured. Here we see a laminar stoichiometric ammonia plus DMM in air flame at 5 bar. From these images, we can calculate unstretched laminar burning velocity as well as Markstein length. The turbulent flame shown is an ammonia flame in oxygen-enriched air at 3 bar. This is the Chemical Kinetics and Laser Sensors Laboratory. The 2 shock tubes are designed to study fuel autoignition chemistry and elementary reaction rates. We can assess pressures beyond 100 bar and wide range of temperatures. Various laser diagnostics ranging from ultraviolet to mid-infrared range are employed to follow the evolution of reactants, intermediates, radicals, and products. Simultaneous end-wall and sidewall high-speed imaging helps investigate inhomogeneous ignition. The laboratory also houses a twin-opposed piston rapid compression machine to investigate fuel autoignition at low temperatures. Laser diagnostics have been used to ascertain the validity of homogeneous core in the RCM. An optical combustion chamber is used to study the occurrence of pre-ignition and supernova. New laser diagnostics and sensors are designed for specific applications. Recently, a novel difference frequency generation laser system has been constructed to assess the bending vibrational modes of aromatics in the 12 to 15 micrometer wavelength range. Equipped with 7 engine test benches, the research in our internal combustion engine labs is focused on studying novel concepts and technologies to reduce the carbon footprint and pollutants emissions of the transportation sector. Here, our all-metal heavy-duty single-cylinder research engine is used to study the pre-chamber combustion concept as part of the FuelCom 3 project in partnership with Saudi Aramco. Different pre-chamber designs are being tested and evaluated to identify the key geometry features to reduce fuel consumption, NOx, CO, and unburned hydrocarbons emissions. Our testing setup is capable of measuring the engine indicated efficiency and emissions with high accuracy and high precision. The engine is operated in well-controlled conditions, which ensures the reproducibility and repeatability of our experiments. In this project, our ultimate goal is to improve the efficiency of spark ignition engines while reducing emissions to near zero levels. Our labs are also equipped with 4 optical engine test benches. They are designed to allow full optical access into the combustion chamber through an optical piston and liner made of high-purity quartz. Here, our optical heavy-duty single-cylinder research engine is used to study combustion in an optical pre-chamber. High-speed chemiluminescence and a variety of laser diagnostics reveal the physics behind the observed trends and provide detailed data sets for calibration and validation of numerical model. Our ultimate goal is to perform advanced laser diagnostics to study the pre-chamber combustion. This relies on developing new optical techniques and adapting their operation to the engine environment. Using a near-term Grand Challenge grant from KAUST, the center was able to partner with Sustainable Energy Solutions in Utah to bring their cryogenic carbon capture process to the kingdom. Here you see the 3 shipping containers housing the components for this 1 ton per day CO2 capture scale rig. The rig is capturing flue gas from the corrosion rig and removing both water and CO2 with greater than 90% CO2 capture efficiency. Working with SES, we were able to de-risk several components, giving us confidence to move up in scale to a 25 to 30 ton per day facility. Due to the cryogenic process, we are able to simultaneously remove sulfur dioxide and nitrogen dioxide as well as CO2. We are developing novel direct contact cryogenic heat exchangers to improve the thermal effectiveness and hence increasing the overall efficiency.